Centro di Ricerca Matematica, Ennio de Giorgi, that really hosts us here in this beautiful city, beautiful weather. So I think everything is perfect. And so thanks to Professor Stefano Marmi and Luigi Ambrosio, that are both professors here at the Scuola Normale, and also to Caterina and Luisa. Luisa is the secretary, you probably met her already this morning, so she will tell us a little bit later about the organizational things. And when I read the Centro di Giorgia, for me at least, I thought, oh, who is Ennio de Giorgi? I'm not a mathematician, so I don't know if you know him, so I asked Wikipedia, and this is the answer that they gave me. I think so. We are here. So he's a famous Italian mathematician. Was born in Lecce and he died here in Pisa. He also worked here at the Scuola Normale, and he's a descendant from a noble family from Republic of Venice. Yeah, welcome. Let's see if they start. So I'm glad that you came here. So this is now the third workshop of the 6 weeks program. Tatjana, yes. So yeah, we are in a wonderful place. This is a wonderful painting by Raphael, the School of Athens. Maybe this will be later on referred as the School of Pisa, who knows? And so, this workshop is now about, as I said, multiscale modeling and simulation to bridge molecular and cellular scapes. So I think we have excellent speakers here, and we will surely see great talks. So if you have any questions, you can either ask me or Jerome, so the organizers. Kevin Barrett from Oxford was also supposed to be an organizer. Unfortunately, he got seriously ill, and so he cannot be with us this time. So hopefully it's better now. And then also David, who organized the whole program. So he will be here probably tomorrow afternoon or on Wednesday morning. And so I think, we have also some students, I think, here that will present some posters. So please, I don't know where exactly, we'll see where the posters are, in which room, but then this also, we'll see, and then so you can go there, have a look, and then discuss it. There will be no poster session, but the poster will be around, so you can go have a look and then discuss with the people. Since we are not that many, that should be no problem. And so we are a little bit late already, so let's go a bit quickly. So many thanks to the Venice and Ragusa, and he's known for working on partial differential equations. So he worked on the 19th Hilbert problem and some minimal surfaces, so where he got also some numerous prizes for that. And what I particularly liked, there was a quote from him. So if you can't prove your theorem, keep shifting parts of the conclusion to the assumptions until you can, which sounds quite promising. And so I thought this is maybe interesting to know, at least we are here in this center, who is the mathematician behind. And so some remarks. Okay, there's the sign for the video recording. So the sessions will be videotaped. So please, you have to sign for a formal reason that you are okay with that. And so there's Wednesday afternoon is a free networking afternoon, and so the rest in the evening, but Luisa will tell us a little bit more in a second. And so if you have any question, please ask Luisa, or I don't know if Caterina as well, for some financial and administrative issues. And so there's a thing here, the program here. This afternoon there was Simone Melchionna was supposed to speak at 2. But unfortunately, he sent us yesterday an email that he's sick, so he cannot attend. So I would suggest that we just shift the talks, if the speakers are okay, so that Simone starts, and then we have Andreas. But since we are late, probably let's see when we finish here. So I think we have a lot of time. So maybe we start then at 2:30 or something like that. So people have at least 2 hours for lunch break. So probably now we're supposed to finish at 12:15, but since we are already half an hour late, so maybe we'll finish at 12:45, and then we start at 2:30 for the afternoon session. So we'll see. This is okay. So Jerome, said everything. So okay, Luisa. So please, just give us some. Also looked up a little bit. So he is now associate professor at the Department of Information Technology there, Uppsala, and also looked up a bit. I was surprised you were, before you started your academic career, you were a developer at Comsol.
Yes.
For almost 2 years or 1.5 years.
Yes.
Right? Similar, because I also, before I started my thing, I was working for companies after my PhD. That was something in common. So then you did your PhD from 2002 to 2008 at Uppsala, I think. And then you did some postdoc at the KTH, I think it's in Stockholm, or where is this? And then you worked at the Linear Flow Center in micro and complex fluids projects from 2009 to 2010, 2014. You're assistant professor at Uppsala, and since 2014 you're associate professor there. And so, so you're interested in scientific computing, numerical analysis, modeling, and high performance computing, so I'm looking forward to what you will tell us. And so here the talk today is, you don't have it, from the bottom and up, bridging the single cell with cell population. So I'm really curious about what this will be. And so, now it's up to you, Stefan.
Thank you. Thank you very much for the nice introduction. And yes, it's true. I have my background is perhaps earliest was in numerical analysis. So you mentioned COMSOL, so finite element software. And also my PhD was with a specialization in numerical analysis, so slightly more to the mathematical side. When Adelinde asked about are there any mathematician, I took like a half a finger up. And then she asked, are there any computer scientists? And another half finger. But I'm not a biologist or a physiologist for that matter. So a computational model is what I do mostly. I try to bring things into some theory, some mathematical theory. I'm interested in the high performance aspects as well, because it turns out, as I will claim at least, that typically performance is quite important. Things have to be fast in the end. Adelinde had some questions concerning parameterization and the fact that you tend to run your model many times over and over again. Some days you do it manually and you want to look at the result and try to fine-tune it, and other days you do it automatically, but still it has to be fast. So I'm going to talk about some concerns and some ideas about how to go from the bottom, and my bottom there will be this single cell, fairly detailed model of a single cell, and try to bring this computational physics all the way up to a cell population. And in the simulations that I will show you, a cell population is something like 1,000 cells, but of course in larger applications you could well imagine maybe 1 million cells, I don't know. Also on the single cell scale I will show you quite coarse models there, but I have previous experience with finer models, so consisting on the order of, let's say, tens of thousands of voxels. So Adelinde mentioned this next subvolume method, and that is a bit the framework that I will advocate here. So this is the outline. I will give you some data. So these are some movies. I have some collaborators at Cell Biology, and the nice thing about collaborators is that you can get some movies. And then maybe the not so nice thing is that you get very difficult questions, and you tend not to get the questions you want. So can you prove that the cells do this and that in your computation model? And of course I am bad at proving biological facts. So I will do some computational modeling and then some analysis within the framework to show that it's possible to actually estimate the effect of perturbations. So if you perturb rate parameters, for instance, you want to ensure that the outcome stays close, or else it's going to be very difficult to parameterize the model. So this is fundamental results. And then some worked examples where I try to highlight the different things I have said during the talk, basically. So this is joint work with an input from Mia Philipson, Gustav Kristoffersson. They are at Cell Biology. Ruth Baker, Dan Wilson, they are mathematical biologists, you could say, from Oxford. Paul Bauer, a grad student who finished just a year ago, so that's high performance computing part. And then two master students that I like to mention, Augustin and Jonas, who have done theoretical work actually. So some movies first. This is the first movie here. You can barely see this purple thing to the left, and that's an implant. So there's an alien body within this live mice here. And what happens is that the defense mechanism of this mice pushes in the neutrophils, so white blood cells. And here they are tracked, a few of them, and they kind of circle around this alien implant. So they follow some kind of cues. It's, yeah, sure, point, a good idea. So I have the implant is what you see here. It's barely visible, just some purple or blue. And then you have these neutrophils coming in here. They are labeled with some numbers, and we are tracking them. So they are doing some kind of movement around this implant. And it's believed that they do follow some kind of gradient of lactic acids, but it's thought that they also communicate together, so they somehow talk. So they meet and talk and do some things. This is in a mice, so and it's in vivo, so the mice is alive. And actually these, it's an implant of some insulin producing cells. So it's taken from the mice itself, and then it's put in a muscle. And it's thought as an idea to look for producing insulin producing cells in the body in other places to see if you can do things like that. It's thought to scale up also to humans for diabetes. So this is a live mice, and there are two squares here, there and there, and they are there to try to track, so you kind of keep the plane, because the mice is breathing and you have a heart and so on, so it's kind of lots of noise in this data. So we try to get accurate data out of it. But you can see this is what 10 trajectories I'm plotting here, then we have maybe 100, but they are very noisy, not so much data and not so much knowledge, and it's the research question is kind of here. It's not really a question about computational modeling. But some data for inspiration. Here's migrating cells. Here in this picture you have an implant over here, the red one, and then you get this kind of gradient to the left, and the neutrophils are the green one, and the purple one, they are macrophages. So they are kind of sensing this gradient within the body and are able to kind of crawl towards this target. This you can kind of make up quite simple a model of, because how cells sense their environment, that you can kind of quite easily discuss. A third example here, these are stem cells. It's a bit dark. This is in the colon of a live mice, and you're zooming into one of these colon crypts, which are kind of a crypt where the cells, you have cells in the bottom, and they divide and pushes the cells upward, and then when they reach here they quite quickly let go and are moved away. So this is the way that the colon kind of keeps fresh cells towards whatever food and stuff that passes by here. They kind of push novel cells all the way all the time. And that's also a kind of a thing you can actually model how this works together. And fourth here is quorum sensing, and this I just took from the citation here. This is 8 years old now. So this is a population of E. coli bacteria. So you're releasing them from this chamber here, basically in the beginning, and you see here how it quickly goes larger, and then it reaches a certain critical population size, after which quite simple synthetic circuit which has been implemented here is enough to make this population sense itself or sense its own magnitude, and you indicate this through these phosphorylation, so these cascades which flashes. So at a certain large enough population it starts to sustain flashes throughout. And if you could estimate, maybe across here you have something like 400 E. colis or something, so it's quite a large population in terms of computing the way I see it. But of course in nature this is a very small microfluidic chamber. So sorry? Yeah, why do they flash? That's an interesting, yeah. No, basically they secrete a small substance, and their neighbors are able to sense the secretion of this. And once they reach a certain critical threshold, they start to flash. So in the beginning, where the population is too small, you haven't reached this critical threshold yet, and you see no flashes. But once the population is large enough, you get these sustained flashes throughout.
But it looks like they are periodic.
Yeah, you get like a wave phenomenon through the population. So that's correct, because there's a finite speed of information, so it cannot be simultaneous everywhere. But you get this kind of wave-like phenomenon. That's correct. It's quite nice idea.
It starts in the middle and then later on it just comes from the outside?
Yeah, there's some inference or interference. You could see that like it's a flash going waves inside, and it's very interesting. Yes. So the modeling challenge: how to think. I want to have some kind of framework where I could do both realistic and useful computations. So computational models of populations of living cells. So realistic, several of the questions for Adelinde's talk were of this kind, that did you take this into account, or what is the rate constants, and how do you do the approximations and so on. And so the way I see it is that realistic means that it should be flexible and you should understand what are the trade-offs. That's what you could hope for. And then at the level of modeling where you are, in some perspective, you should be able to put in whatever relevant things you would like to put in there. If you think that we need a diffusion, you should put that in, be able to put it in. If you think you need crowded diffusion or excluded diffusion or something like that, you should preferably be able to do some work and put it in. So flexible is quite important here. Also useful, and that's when you work with cell biologists, that's a difficult thing, because yes, from my point of view, I would like model to be fully explanatory, so it should kind of be bottom and up. You should build from the physical level of description and then be able to capture some emergent behavior at a much higher level of description, which you didn't code there from the beginning, so it's kind of emerge of itself. But on the other hand, you also want to test hypotheses. So in the case of this quorum sensing, maybe you don't know exactly how it works, and you want to test some different quorum sensing models and see which one is the best one. And then maybe that goes against a little bit this full explanatory thing, because you want to test on in some way on a convenient level, where you just fiddle with the stuff to see how it fits. So then sometimes to build fully bottom up can be very inconvenient. So predictive value, number 4 there, help to build an argument in cases where many factors are unknown. This is the biggest nuisance, I think, because you have some image or some video, and actually the research question is, what is going on, or what is the mechanism behind this? So you don't know, that's the thing. And I would like to model it, and of course I need to know what to model. And now you're talking about somehow fluid modeling everything at the same time and try to pick the right pieces out. So I wrote here that number 1 here, this explanatory issue is about mainly modeling consistency, that you understand the stability of the modeling framework and the things that you can express, the modeling power. And so it concerns those issues, whereas 2, 3, and 4 here is about being able to take some data and put it into the model somehow. And I think that it's also about simulation performance. It looks like it's a whole different issue, but I think it's the same. If you want to be able to incorporate data and test many times, it has to be very fast, actually, very, very fast. So these are the kind of things that goes in slightly different aims here. So the risk of over-modeling. I wrote on the previous slide there that I would like to help to build the argument in cases where there are many factors are unknown, because actually what is going on is the question, and I should be able to, through the modeling, help build an argument that it's this mechanism and not that one, or if you do it this way and this way, it's much more, the effect is stronger, or something like that. So you might end up taking all of these very many complicated things, and you take a super detailed image or whatever of a cell, and the question is this really detailed, or are you imagining that you have some accuracy because you have a fancy stochastic model of some kind? Or is it just a kind of plain overfit? So this is a line with some small noise. But of course you can fit exactly a very high order polynomial to it. But that's a kind of important balance, I think. Moving on, so the rest of the talk, I will talk about computational modeling and this idea to aim, based on this previous motivation, to aim for a single framework, a kind of notation where you write it down and you can meaningfully talk about errors. You can meaningfully talk about perturbations or changing rate constant in a consistent way. And scalable I put there in as well, because it has to be able to perform. Maybe not the first implementation, but maybe the second or the third. You should be able to imagine that it will be fast in the future. Will do quite quickly actually some numerical analysis in that very framework, and then I will just illustrate some applications. So the computational modeling, this is the first step, the inner-outer idea. So you have a cell here which might be very detailed, and the step to go to a discretization of that same cell is what we do in this reaction diffusion master equation, which I will just talk about quite soon. So going from the single cell, a detail, you do some discretization using a computational grid. And then the same idea is for the cell population here. So I have an image of the cell population, and that very cell here might be this one here. And that is supposed to capture the physics of the cell population. Many cells crowded together, signaling or touching each other or saying things to each other or dying or proliferating and so on. So the immediate idea is to describe the individual cell. I call this the inner scale, and I couple it together with a kind of population level model, so the outer scale, so inner and outer kind of idea. And the challenge here is that I'd like this to be written as one single framework, because I need a kind of notation where I can meaningfully track uncertainty propagation and changing rates and so on. I do some errors. I would like to see in a meaningful way what comes out of those errors. And also this issue of scalable. So in this framework, you have really inner workings of a single cell, sensory input-output, the space outside the cell, and the population mechanics and how the cells do things together, and preferably quite fast. So these are you have to trade off somewhere, obviously. One model to rule them all. Yeah, I came early on to work with the reaction diffusion master equation, and to a hammer everything is a nail. So that has been a background experience to me, and then I tend to see RDMEs all over the place. But it also has to do with finite element methods and finite element discretizations, actually. So it goes back longer than that. Basically, if you have some complicated shape, you can do quite high quality meshes of that, triangulations, and you get nice compartments, and you can start doing physics in this discrete space, or space discrete world, sort of. So the real world property here that you can capture is that you have noisy stuff. You can see from the videos that they are noisy by themselves, and the cells are blurry and they move in a kind of a bit chaotic way. You also have species discreteness, so there's either one cell or 0 cells within a voxel, or maybe 2 cells. And if you zoom into a single cell, within a voxel you have 1, 2, 3 proteins or DNAs or what have you. And it's not 1.3 or 1.4. And then, as Adelinde draw this picture, when you have some gradients going on, that you need to do something about the space. So grid-based. So you have stochastic, discrete space, and grid-based, and that so happens to be the RDME. So in this way, I try to motivate that it's a good basic choice. So this is a spatial continuous time Markov chain, and usually called the RDME, reaction diffusion master equation. Although the master equation part is a funny name convention. So here's how it works. This is the inner scale. I do some kind of simple triangulation of a cell. That's a toy discretization. Usually you can do quite fine. And you have reactions and you have diffusions, like in Adelinde's talk here, basically. and you have rates. You associate diffusion rates, reaction rates with those events. And together, that gives you a continuous time Markov chain in space. Because the rate, they tell you how quickly these events are supposed to happen, and they tell you when. So you just repeat, you pick a random number, you sample what event happened and when, and you move there and you execute it and move on. And it's quite simple. We also have experience with parallelism in this framework, and it turns out that it scales pretty well. It's okay. So actually it's quite fast. You simulate, I don't remember exact figures now, but almost 0.1 giga events per second. And if you compare it to gigahertz, that's pretty good. Gigahertz processors, that is.
So you're solving a system of rate and diffusion systems in the cell?
I would rather phrase it that I simulate this Markov chain. So I sample a Markov chain at a time. So simulate if that is to your meaning.
Markov chain for what?
For reactions, all kinds of local reactions. A reaction takes place within, let's say, a voxel, a local non-linear event of some kind. And then you have diffusion, which goes out of the voxel, and which is more of a linear first-order event. So all of these things couple the model together in a if you go for PD, it would be a reaction diffusion PD. But then it's deterministic, of course.
My question is it a single or is it a system?
If you mean several species, yes, of course, many species, yes. Was that answer your question?
Yeah, because you're saying fast, but it's relative to how many equations.
Yeah, of course. If you add 1,000, it will take more time. Of course.
It's relative.
Yeah, sure.
The discretization can be automated, as I said, but does it also change during simulation? This kind of discretization?
So the answer is that, of course, it can change, but I have not been doing changing discretization. I mean, it's a lot of lookups and bookkeeping to change the mesh. It's the same for PDs if you have adaptive meshes or something.
If you have like these kind of irregular structures.
Yes.
That is then really, yeah, because of course everybody knows how to do this with meshes, but that looks a little bit more artistic, what you're just showing.
Yeah, this one.
So I was just wondering about this, how this would evolve.
Yeah, sure. No, if you're trying on really moving this or stretching, of course, that's then you also have to describe the physics,
and
like some kind of stiff springs and so on.
This looks a little bit like if you have like the vesicles and so forth, like in your
moving around.
And the thing is, of course, then you need additional information how these can then behave. Yeah? And I think that is.
I think you're right. That this is more to the artistic side for sure.
Okay.
I mean, it's doable, but it's a matter of actually building such a model and use it for something. So this is basically what was implemented some years ago in this framework, Uhrmacher.org, speaking about free software. It's in version 1.3, and I'm about to increment that with 1.4, and then several of the models that I will show you will actually be available there. It's in MATLAB and C. So speaking about languages, someone asked the trade-off of being easy to use versus fast, and this is you have to know a bit maybe of C, and it's not just a kind of abstract click and drag. It's for high performance computing, so you are supposed to know what you're doing in this way. Anyways, that was the first idea, and then the question is could you do a kind of RDME? Like I said, to a hammer everything is a nail. So is there a RDME at the cell population? Because I want to go to the cell population. Can I somehow do an RDME at the cell population? And there are several differences because cells are autonomous objects that are kind of together. They can't just diffuse freely, and because that would mean that they kind of die. And they also move, so they have some kind of pushing it around each other. They have some mechanics, and they might crawl, like you saw in the movies. They crawl towards a gradient. And they also experience adhesion, that cells actually want to stay together. They don't want to just move chaotically across. They want to kind of bundle up a bit. So there are some effects that definitely did not go well, doesn't fit directly to the RDME framework. But then the second idea here, the outer scale here, that I'd like to advocate is where we consider such a mesh to the left there, and I consider one of these voxels, the one in red, to be occupied by 2 cells. So you can see the schematics of the cells budding up there, basically. And then I imagine that because there are 2 cells in that voxel, there's a kind of pressure propagating outside. So that acts like a pressure source, these double up or doubly occupied voxels. And the easy way to explain the physics here is by these springs. So you kind of, these doubly occupied voxels kind of wiggle around, and then the wiggling kind of spread. And that will yield eventually a rate over here that one cell will actually move away. That's an artistic way of explaining it. A better one would be to go for mathematics. There's something called Darcy's law, which governs the flow through a porous medium. And you can imagine that the pressure here is flowing through a porous medium, basically, and you get cells that move at the boundaries here. So they are driven by this gradient in this pressure. Yes, please.
I have a question, because you are now getting together some kind of, sorry, very interesting. So you have, on the one side, you have these, more or less, these concrete things, like the cells, yeah? And then on the other side, you have these NSM, as similarly what we did in ML space, but there we used like rigid, of course, objects. You're using here deformable, and also with springs, you're using a force-based approach here. I think, how do you, when you are, like for example, you are now, you have these 2 cells, and is it so that each of those, how do the cells, the size and position of the cells influence the reorganization then on the NSM or the, what you there have? So because I assume, and then the 2 of those, they are then departing at some point, and then they should kind of like, also the mesh below that or whatsoever has then to adapt. How do you, but maybe you're coming to that point. But
thank you for the question, yes. So this is rudimentary explained, and it depends, of course, what exactly would you like to capture. So here I just show you a static mesh, and the mesh is the same, it doesn't change. And then it's either, let's say, 1 or 2 cells in each voxel, and that's, or 0, it can also be empty. And then if it's 1 cell in each voxel, then that means it's a static equilibrium. But 2 cells, it means that you get a pressure source. And then to your other question concerning these springs and forces, and yes, that is correct. But the nice thing here is that the equation that comes out of it is actually only the Laplacian. So I need to solve the Laplace over this mesh, basically, and the red voxel there will have like a unit source. And that's the physics of springs. It's very nicely goes into Laplacians for some reasons. And then your other question you asked also about what if there's like a cell cycle, so they have different volumes and so on, and that you could also in principle do by saying that you have a cell which starts to be large, and then it will be a small pressure source and so on. There are several ideas, but in the models that we have looked at, this came up actually in a master's thesis for a tumor model, exactly that issue. You had a cell cycle. And then we found that you're very quickly go to over-modeling. Because whether you have a cell cycle with 10 states or 1 state, it doesn't really affect the data you have. So it's like very difficult to actually say that you need that kind of accuracy. And I think it's close to imagined accuracy, actually. Like it's not really there. But there's one slide about this physics again. So there are 3 basic assumptions here. I completely ignore thermal movements. So the cells, or they might be kind of doing some small local Brownian path or something, I'm ignoring that. I say that they are still. And I also say that there's a rapid equilibrium of pressure. So if there's a doubly occupied cell over here, for instance, it would quickly equilibrate throughout. So the pressure, the cellular pressure here, which is the driving mechanism for movements, it quickly equilibrates. So there's no wobbling or that I have to be quick about some event taking place. Just the final one. And then also I put a rule that I want to avoid arbitrary movements around here. So I say that you can only move into a less crowded voxel. That's a specific rule, I say. So these doubly occupied here, they can move here, and these one on the boundary can move out here, or so on and so forth. So all the arrows there that you see at the boundary and in the middle here, they are all the rates that I need in this simulation. They are all the events that can take place. Okay, there are many questions now. I think you were the first, sir.
So which kind of cell you want to model? Because, for example, some cells are polarized, and this is a crucial property that seems completely absent in your description.
What kind of cells?
Yeah, I mean, some cells just move. They have a front and a back polarization.
Polarization, yes.
So that is missing.
Yes, it is.
So there is also persistence of motion in a direction. I mean, so all these features that are quite important are completely missing here.
That is correct. So if we take polarization first, for instance, here is kind of rotationally invariant by just at least by the picture, of course. But then in practice, there will be a tumor model that I will show you. There is actually a direction, and they are moving outwards in that particular one. In that case, you can get away by having a simple rule saying something like first in, last out, because it follows the direction of the flow. If you have more difficult polarized situation, you might need to keep track within a voxel. What does it look like? Is this cell from that corner, and then if you have an event over here, maybe it's that cell. So in that case, you might to add some extra degrees of freedom to describe that movement. And then you mentioned also persistent of movements, and that's a similar thing, that you need some kind of arrow and remember that arrow. And that's for sure, if you have a gradient, for instance, that you like to crawl upwards, you need to do more detail.
Without gradients, I mean, cells are persistent.
Yes, absolutely. And there were some, Jürgen, I think, was the second. I'm chairing here.
I just wanted to know this rapid equilibrium of pressure. I mean, this is something, of course, it helps to assume equilibrium, but this is something that you actually also measure, because I assume if you're inside, it will take some time, because equilibrium of pressure means also that somehow the volume changes, or the whole population has to somehow increase at some point. And then the third point, movements into less crowded, is this not a consequence of the pressure? Basically, you have to impose this, or is it not? I mean, you would assume that physics, if you have higher pressure, it just moves into.
Yes. So there are two questions. I think the second one is more difficult, actually. But let's go for the number two there. If you think of it, if you have a proliferation event, so you have some cell cycle going on, and then cell is actually proliferating and becoming two. If you take that time scale for this event and you compare, it's fair to say that there's an epsilon of scale difference, and the pressure is, compared to that, rapidly equilibrium. So number two, I don't think is such a bad assumption. But number three is a bit more ad hoc, because if I take that away, I will have rates all over the place. I will have cells moving all over the place. It might be a small rate, but there will be a rate all over the place. And then I will also have a breakup of the cell population, because as long as there are sources, they will move. So you're right that there's a thermodynamic kind of thing that you should move in that direction. You expect this to happen because they are autonomous objects, and they won't push into the next just because there's a small pressure behind. But it's a bit built into the discrete physics here. Maybe the correct way to say is that I build this discrete world, and I try to ask myself, what is the best physics that I can do here? So it's part of this comes from the continuity of space, and I have a grid to take care of. So it's right that when you reach questions about continuity of space, and like, can you have a volume 1.1, 1.2, and so those are things you need to stick with the discretization. There was also a question over here. Yes.
Yes, so just a few questions to make sure I understand. So do you only consider isotropic stress like pressure, or do you also take into account shear stresses like your spring might have suggested?
Yes. No, straightforwardly, I only consider isotropic. So the springs that you say, they are the same in all directions. You could also add anisotropic pressure, and that gives you then pressure tensor to your Laplacian. So instead of just an isotropic Laplacian, you get some tensor in there, and you need to have some kind of measurements of what to do. But I have not tested anisotropic pressure-driven moments.
Another question. It seems to me that 2 and 3 are incompatible in the sense that motion, at least, you know, if you just look at fluid, comes from pressure gradients. So you say pressure is uniform and the motion to less crowded voxels. Why don't you just couple crowdedness to pressure so that you'd have motion driven by pressure gradients towards less crowded regions?
Yeah, that's a good point. I think I also saw some modeling to that effect, but this was done in PD language, so it's completely continuous space. But you point to a good, this is true, like the rule number 3 there is to make it fast, mainly. But it's true that should, for instance, this cell here, should there be a rate to move here? So there will be a hole then. And then actually this one will be doubly occupied suddenly. And then there will be a pressure source, and it will typically quickly move back again.
Okay.
So
it's a question of efficiency rather.
Yes, it is like, it is for sure. And it's also taking into account that at least I have difficulties to see that the physics should be such that they move into already crowded voxels.
Right. So maybe this points to my last question. So you mentioned Darcy's law,
yes,
which is flow in a porous medium, but the porous medium itself is static.
Yes.
While flows of cells often they are closer to, you know, the physics of foams, where motion are due to transitions like T2 transitions, where exactly cells have to move around so that one cell can move through.
Yes.
You ignore this completely, or?
Of course, I don't want to say that I ignore this completely, but yeah. So I don't know if it's a good answer, but the grid is fixed here, and it is what it is. You can have empty voxel, or there could be 1 or 2 cells, and then the question is, what physics can you do? And these questions about polarization is one issue for sure. You can also have. I will show you an example later, where you actually have an identity on the cells. So they either have a red or a green gene, and they are not the same. And that's a bit the same as this issue with polarization. But for sure, you can add, and in the end, I think you end up with a similar thing, but more of the kind that is an agent model. So here is still kind of a counting model. But when you start to add more attributes, you end up with a more detailed agent-based model. Thank you for many interesting questions, and please, I have no poster, but please talk to me later. I would be interested in arguments like these. So from these basis assumptions, I get a Laplacian. It's a discrete Laplacian, and it's actually the one associated with this mesh. So it's the same Laplacian as that. I don't need to do a more accurate one. It's that one. I have certain boundary conditions. I have a layer out here where I have a Dirichlet boundary condition where the pressure is 0, and I have source terms for all of these voxels where I have doubly occupied cells. So that will spread evenly out, and I will see some gradients at the end where the cells will pop out basically. And this gives me rates. The rates are just proportional to the gradient of this pressure, and when I have rates, I have events. And like I said, to a hammer, everything is a nail. So this actually becomes a kind of master equation, or a spatial continuous time Markov chain. I call this DLCM for discrete Laplacian cell mechanics, because the Laplacian is so used over and over again. And one point in favor of that is that the Laplacian is very well known how to effectively invert it. There are many techniques to very quickly invert a Laplacian. So multigrid, algebraic multigrid, algebraic multi-level methods. There are various types of iterative methods, and so on and so forth. So it's very well known numerical techniques to invert the Laplacians. It's tentatively very fast. Coupling of scales. So the first observation is that you have an inner scale here, potentially an RDME for each cell, but it could also be an ODE or an SSA or something like that. And the outer scale of the population, and they are formed in continuous time now. So I have an RDME, an ODE, or an SSA or something like that for each cell. And the DLCM methodology take place in continuous time. And therefore there is like a mathematical ground zero. It's in continuous time. They should occur in the same continuous time frame. So that I could say is what is meant by coupling the inner and the outer scale correctly. That's like the origin, basically. Observation number 2 here, that these two types, the inner model and the outer model, they can be expected to take place at different temporal scales. So usually the kinetics of a single cell will be faster than the cell population, of course. And you can think of an approximation here that you evolve all of these inner scales, all of these RDMEs or SSA or what have you, one step in time, for instance in parallel. And then you connect at this outer scale, which would be the cell population scale, and you would hope that there's a scale separation taking place so that this is still going to be accurate. And in fact, you can think on all sorts of computational tricks like this. So similar ideas, or you do a bit of an ODE, or you do some things where you try to do things nested or hierarchically, and so on. And often, typically, you accept some kind of small error for computational efficiency. And then, of course, what is meant by small. And that brings us back to the situation where I would like to meaningfully analyze the error, or to explain or to make it believable that its error is going to be small. So, analysis message here. So typically you want to use these kinds of models when either one of stochasticity, species discreteness, or spatial inhomogeneities make a difference. Or else you could just have an ODE, because then it would, none of these matters, an ODE should do the job. So the model itself is therefore likely going to be sensitive if I perturb one of these. So if I do some assumption, for instance, that species discreteness can be approximated by a continuous variable, for instance, then that will make a difference, because otherwise I could probably go for an ODE in the first place. So a computation framework, I would like it to be able to allow for error estimates of approximations. If I touch a variable or a rate or do some approximation, I should be able to tell what will happen later. So I will do a very quick analysis. This is lots of work went into this, but now I will give you a 3 slides effective summary. So this is for the RDME. I have a notation here. I put a matrix Xij, which is the number of molecules of species I in voxel j. So this is RDME style, but you could use the same kind of notation for this population level, the DLCM method. And I put some suitable initial data and some assumptions. And the tricky issue here is to find those assumptions to make them concrete. And they are actually a little bit of a list. Then you can prove that the RDME itself has bounded arbitrary moments. And you can prove that if you start at the same time with the same state, almost surely, and if you perturb this trajectory yt by doing a small perturbation of all rates, or a rate if you wish, all rates in a relative sense, then you can prove that as this perturbation goes to 0, the root mean square or the mean square goes to 0, so that you have a continuity in effect. It's a sane mathematical model. And the number 2 here is important. Actually, you can prove that if these are a bit more nicer, so you add some assumptions, then you can actually get half-order convergence in this rate parameter. That means that if you have a rate r and you want to test what happens if I go to r prime, a small delta perturbation of r, then I can actually lean on this framework, because it will be a small perturbation in the solution as well. And that in the end is what makes it possible to do parameter inference, because if I have a discontinuity there, it's going to be hopeless. It has to be some kind of degree of consistency with respect to parameter response. As a short worked example here, I do an example in multiscale variable splitting, because the inner-outer idea was of this kind. I try to think that the inner scale is faster than the outer scale. And here I have assume a simple separation of scales, that species are either abundant or in low copy numbers, roughly 1. And the rate constants, they are either fast or slow. So 1, epsilon, epsilon inverse, and 1. And then I can construct this rescale variable where all the species are now of order 1, roughly, by taking a suitable combination of epsilon. And I can consider 2 types of methods. One is this hybrid method with a bar, where I simply replace everything which is stochastic and driving an abundant species with a mean drift term. So it's an OD approximation kind of thing, a homogenization idea, quite simple. And another one is that I do a numerical step on top of this. So now I take low copy numbers and I simulate them according to their dynamics in a time step h. And in the next step, I will take abundant species and do an OD integration of them. So a simple Euler forward or Euler backward or something like that. So there I have 2 types of errors basically. And some results here for certain exponents, and they are explicitly known. And certain assumptions. I can prove that I have a certain convergence in epsilon. So this is the multiscale separation error. So depending how well the scale separation, how strong it is, I will have a smaller or larger error. So it comes out of the theory nicely. And then I have this time discretization error under some assumptions, and I have to add here that the processes are bounded. I can actually get an error in this numerical time step h, so I can understand how, in sense of time step, what is the error, basically. So now this framework kind of allows for a certain degree of consistency analysis, convergence analysis, and also stability analysis. So those were the theoretical results, and this is a very simple example. This does not correspond to a real situation, but it's taken here, so it's a certain amount of nonlinearities, and I have scale separation of species, and it's done to kind of stress test the theory, like a corner of the theory where all different terms are fairly large, or you cannot neglect them. And then the results are basically that it's perfectly according to theory in both this multiscale error as well as in this split step error. So it seems to be a nice theory which tells you what you can expect in terms of how it will evolve multiscale errors as well as numerical time discretization errors. So to conclude then, the modeling framework is basically the RDME at the inner cell and the DLCM at the cell population layer. So starting with the RDME here, I have a number of molecules that I count, the species, and I have reactions in each voxel. So there's a nonlinear reaction taking place within each voxel. That's like an inner scale to the RDME. And I have diffusion coupling these voxels together. And then the DLCM, instead I have the number of cells in each voxel, and I can have an inner scale which is selected from a range. I will test here OD, I can have a stochastic SD, and also an RDME. And then the movement is this pressure-driven idea where you kind of grow your domain, or you can add some active movements as well. So it's clearly doable to analyze this kind of inner-outer RDME, DLCM split-step method following this outlined RDM theory, which was specifically for the RDME case. So, but I haven't done it yet. Okay, so I will end up with some examples, and please feel free to ask questions. The first example here is a very classical example by Kohler et al. From '96, and this is just an OD kind of inhibitor kinetics, and you get this black and white patterning. So here I tested this in a growing population of cells. So it looks like this. So they are proliferating at a certain rate, and then you have this ODE model taking place at the same time. And you can see that the equilibrium was quite slow there. So I tried also to change the kinetics. So this is a faster kinetics now, and then we have a kind of almost equilibrium at any given time there, basically. So you can imagine that you can use this to actually infer the parameters here. What should the scale separation be? So that was just a toy example to see what happens, coupling an ODE with a DLCM. Here is a more advanced a tumor model. So here the idea is, this is taken from the cited paper there, that tumors can have this proliferating zone where the cells are proliferating. Then you have this quiescent layer where they are alive but not proliferating. And then you have a necrotic core, because the oxygen deprivation and the nutrition deprivation and so on actually makes the cells die. So this was thought to be, without vascularization, it was thought to be like a stable equilibrium, that they reach a certain size and they cannot grow beyond that. So we built such a simple model of basically just oxygen take up and then proliferating at a rate which is proportional to the oxygen. So very, very simple. And some ideas of cutoffs for death parameters. Basically, if you are deprived of oxygen for a certain amount of time, the cells die. And this is what happens. So you grow it, now they are red, all of them, so they are pushing outwards, and then you see a necrotic core and a bit stable for a short while. But then you will actually see protrusions form. You see by the end of the boundary, it starts to wiggle. So now it's quite round, and now you get small wiggles. And if you run this for a long time, actually it protrudes all over the place. So this is like an emergent behavior, because we didn't at all code this in. It was very simple rules we coded in here. But if you think of it, when the tumor is able to increase the surface here, it actually takes in more oxygen, because oxygen comes in at the surface. So this steady state on the previous slide, we did not find by this simple model it to be stable. It actually starts to wiggle, and then you get protrusions going away. Yes, there was a question here.
So you have diffusion of oxygen. How is it doing?
Yes, that is correct. So we let oxygens go in from outside, and it's like you say, it's diffuse. And the cells also pick up oxygen, so it decays with the cells.
So this is a diffusion.
The oxygen is diffusion. Yes.
So this instability is mediated by diffusion of oxygen. I mean, it's well known that if you have an interface that grows something diffusion from the exterior. Okay. The tip grow faster because there is.
Yeah. There's something like that. If you have a reference, I would be happy to take it, because we found to the contrary that people said that under these circumstances, these kind of cells, they grow to a stable size and they can't go beyond that. So this was a bit surprise to us, at least. But if you have a different background, some things are very clear. So that's a good remark.
I mean, if you, for example, if you pump air into oil, the bubble will be unstable because there is pressure.
Yeah, no. That analogy could be correct. So Jürgen, I think, was number 2 here.
I just want to know what is this instability exactly. So what you see, this is white, and this is white.
Yeah, so now it's quite round in the beginning, but then because some cells come closer to the source of oxygen, so they have more oxygen, then they proliferate a little bit faster, and you get a kind of protrusions of cell which run away from the others. So that's the simple instability in this very simple example.
This is in the inner core?
No, this is on the outer here. You see that they will start to. That's quite stable actually. It's like a fairly round circle, but it's opens up also with the boundary. There was a question over here.
This is equivalent to a negative surface tension. Apparently, there's a length scale at the periphery. Do you know what this length scale?
No, I have been asked this question, and I haven't analyzed this in a mathematical way. But some suggested, why don't you put like Bessel functions and try to look at the eigenvalues or something? I couldn't tell only from this the idea that some cell goes first and then starts to proliferate faster and then therefore comes closer to the oxygen. So there's a random fluctuation. That's all I can say. Yeah, of course, that would be interesting to understand more mathematically.
In this case, the wavelength is just that you have a diffusion. Diffusion gives the instability, and surface tension restabilizes it. So at short wavelength, you are stable, and you have a maximum growing wavelength. I mean, I think in the usual cases, it's exactly what you say. You start with a round shape, and you compute the linear stability.
No, I think there could be something.
You could, in fact, it's simpler to do it with a planar interface than with a round, because
probably.
you don't have to use Bessel function. You can use Fourier.
Yeah, perfect. Okay, thank you for those questions. Let's move on. Yes, and this is ongoing work also, actually. Speaking about performance and speed, so I had a master student try to parameterize the model, saying, what if we could observe such a tumor? Can we find the parameters of it within the framework? So if you get some data about the growth, could you kind of infer some basic parameters of it? And so these star shapes here, they illustrate various types of summary statistics that you could kind of try to take out in an automated fashion. And then you would like to see, can you within the framework itself actually determine the parameters? And here there's this parameter is fairly well defined because it has a minimum here in this summary statistics distance, basically. So I can find it quite well. The other one here is slightly less well determined because it's flatter to the upper end. But this is ongoing work. It seems to be doable. And in order to produce these types of response curves, of course, you have to simulate many times. But still doable, actually, on a PC or smaller PC. Here's a nice use of this framework to actually understand what is going on. So this was 2007. They put a drop of E. coli, and there's a red and a green one. So there's a mutation, and you can see it directly. And in the beginning, of course, there's just a random mix, this drop, and then they grow. And then basically, if there's a red one which comes to this part first, it will be red after that, because that's the sort of mother of all the reds in that sector. And here there's a green one which eventually won here, and then actually kind of get a sector of green ones. So there's a colonization process here. And I tried these very simple rules, and actually it's nice to see that you actually kind of understand in a way what is going on, because you see it with your eyes. It becomes very concrete. And here's this only one flag, red or green. And if you're red, I plot it red, that's it. And then the physics just do its own work. So it actually gives you a kind of intuitive feeling here. I think it's nice. Final example I will show you is protrusions-driven delta notch. So here's this observation that you had a high delta. So this is a pattern formation mechanism, and it takes place, so you see that there's something like 6 or 7 cells in between, so it's like a long range pattern, and yet overall quite regular, so it's like a checkerboard patterning taking place in quite some range. So that's an interesting thing to take. So to test this framework fully, I actually discretized each cell here with a RDME, so it's a small coarse mesh. And then I have a population, and then the idea is that the overall kind of end discretization would look something like this, because I have the same discretization of each cell everywhere in a way, and I couple them together. So that would be the grids combined, basically. And then protrusions, so it's observed here over time. There's a time scale here, and they have a protrusion where they kind of go out and go in again. So they touch each other, and they emit some kind of signals here. And the model I selected for that is a simple model where you basically have a protrusion length and you have an opening angle. So you put out some protrusions in a sector, basically. And you get quite many different types. You can have direct contact with your neighbor. You can have protrusion mediated, where 2 protrusions meet. And then you can have these kind of isometric ones where a protrusion touches the membrane directly, or vice versa, where this membrane here touches that protrusion. So you can have an asymmetric kind of communication there. And this is what it looks like. So the traditional example is this one, where you had something like 6 or 8 cells between, and it equilibrates quite quickly. So here's a RDME coupled with DLCM to see what you can actually do with it. It's quite expensive to do in total, but in the end it becomes a movie. And then you can have weight the signal slightly differently, so you get different kinds of patterns. So here you have you weight the protrusion signals differently from where you touch immediately, the junctional based communication. And you can also have polarizations, so you have protrusions only in certain directions or along gradients if you wish, and you can get kind of tiger stripe patterns. Or you can have protrusions in the direction of growth, basically. So you get this kind of jellyfish kind of patterns.
Sorry, I missed what you said here. What is actually red?
The red is high notch, high delta, sorry. So it's one of these proteins later thought to, do something. For instance, induce hair growth. That's where it comes from originally. But these patterns, of course, they could also, do a zebra stripe or whatever, or angiogenesis. So vascularization could also be an interesting thing. Like, where should they grow? How? So that's my final slide. I showed you some data, microscopic data, some movies. That was mostly for inspiration. And I talked a lot about how to think, flexible, understandable, and fast. And then I proposed this inner-outer scale idea, RDME, DLCM, and this consistency notion of consistent coupling through time continuity, and this quite fast event-based computational framework. I did some analysis, not much, but I just showed you the basic ideas, and it's doable to also bring this kind of analysis to this combination. Finally, I showed you some examples, and all of these were in Uhrmacher, which is available on GitHub. And there will be version 1.4 quite soon, and those examples will be implemented there. Thank you very much. Thank you for many questions.
Yeah, so there
are more to come. So just to get a feeling, what does fast mean for the example that you showed with this delta notch?
The final examples are by far the most expensive, because I have a population of 1,000 cells, and each cell is 40 volumes large in terms of RDME. So then a number of events simulated for this is something on the order of hundreds of billions. It's quite big. And how long does it take? I think one of those by the end takes 24 hours each. So that's quite big. But in the parameterization process for that one, I took simpler models before that. For instance, I replaced the RDME with a well-stirred model. And then it takes something like just an hour or something. And then going even further to an ODE, and then it's done within a minute. So I could do a lot of the parameterization issues on the earlier level and try to bring it to the more difficult levels by the end, actually.
Thanks.
Okay. Yeah, thank you for your talk. I was wondering, you have the RDME you have within the cells, right? And then you have these other approach where you say, okay, a cell can, or more or less, you have one cell, two cells within these kind of like places. How do you cope with these kind of extracellular matrix and things that are happening outside the cells, which are also very crucial, of course, and where I would have first, when you presented it, I thought, okay, you will have also something like an RDME similar approach also outside the cell. So that was, yeah.
So there's nothing that tells you the answer here. You could do however you like in principle. If you couple this somehow with an enormous RDME, it becomes very, very expensive, because then you cannot decouple. So the nice thing now is that you can decouple it and run it in short bursts in parallel, of course. But we had one such example, which was a very advanced tumor model where you actually have extracellular matrix and you had to keep track of it. But in that case, the physics for that one, and also oxygen or lactate was there. But the physics for that was just a PDE. So you just ran that alongside, like a backward Euler step in between, sort of. and that was much slower than the rest of the dynamics, basically. So if it's okay with a PD, for instance, you could just make a few Euler steps in between and update that solution, and then that would be the source term for some kinetics within the cell.
Okay, thank you.
Yeah.
I have a question about the actual result for a change.
Which one?
Of the tumor growth thing. So
yes, okay.
my question is, how sensitive is it, this kind of uneven growth, to the rates, well, of cell growth versus nutrient access? Because I think tumors are actually known, like skin tumors are known to be very irregular shape, and that's what separates them from benign things.
Okay.
And I think that's rate of growth must.
Like
you probably captured that.
Yes, we have
model.
growth curves, but we have not attempted a mathematical explanation. Like, is there, for instance, we think that there's an initial exponential growth followed by some other law, which is probably linear or something like that. But there's not a plateau. That we never reach the plateau, because then eventually you get these protrusions, and then you actually kind of increase again a little bit.
Keeps increasing the surface.
Yeah, and then it breaks up actually in pieces. So that's what happened. You actually get
right, but does it depend? Does it depend on the relative rates of cell growth and nutrient access, like oxygen access?
Yes, it does so. So these were ideas to try to see the response of certain summary statistics. So here is some convex hull property, but we also did time series like autocorrelation in time and so on to see which one were the good at identifying those parameters. So if you have a depth parameter or an oxygen speed or what have you, diffusion constants and so on, you would like to see that the end result is sensitive or not to that. So these were part of trying to figure out, and we found a few parameters which weren't really identifying themselves. As long as they were above some threshold, we couldn't see them. There was just a flat line response, basically. So we could sort of get rid of a few parameters, but we could also see the ones which were more clearly identifiable.
But you were getting these irregular shapes with any kind of parameters. That's
irregular, yes.
Irregular shape.
Yeah, we have never been able.
Does not really depend.
The only thing we have been able to do is to delay the process to make it slower. If we want it to be sort of confined and nice, we need to add some extra process. An example would be adhesion, that the cells want to stay with their neighbors, so they don't go outwards. So you need to actively add that as an extra process. And if you start from scratch thinking of it, you might not come up with that idea. But when we start simulating and try to make it stable, we see that there's no way we get it stable unless we kind of make them crawl backwards to their home, sort of. Otherwise, they will go out.
Oh, thank you. Interesting.
Could you, by any chance, comment on your given experimental data? Can you? Yeah, you did. Oh, sorry.
It's okay. I can hear you.
So can you? I wonder what is the ground truth. Can you validate this with some real data, experimental data, where you have rates that you try to mimic, try to recover in some sense?
No, that's a good question, of course. Let's take this tumor model. Here, the experiments that I show you are only taken from the kind of the simplest mechanism we could cook up with. Like, take so few parameters as possible and cook up a tumor model to see what happens. And then we have tried and cross-validated it to much more advanced tumor models which have appeared and even tried to be parameterized. But we think that there are quite a substantial amount of modeling going on which is over-modeling, because although we have maybe 7 parameters and they have 27, it's unclear if you're really doing things more accurately. More closer to the truth maybe, but the end result is it's not clear that you have data that supports it. But then the other ones, I showed you this pattern that have been more well researched through. So there starts to be a body of evidence roughly saying how you should wire these circuits and what kind of things you should compare it to. So in that sense, it's more closer to something that actually happens. But that's part of the thing, that these computations take place in an environment where actually part of the research question is what happens. We don't know what happens. So it's like a PD with unknown terms. We don't know the terms. So that's part of the question, actually.
That's right, but I mean, can you give confidence to the parameters that, how much confidence can you give that these are the rates, these are the right rates?
Here I can't discuss that at all. The only thing I could say is, are they identifiable or not? So if I were giving data, could I actually identify the parameters? And then the answer is that in some cases they are well identified from potential data, and in other cases there's a flatline response and you actually cannot really select it because you wouldn't see the difference.
So, other questions? So if not, okay, let's thank the speaker again. Our interference. And, I think somebody's coming now to get us for lunch. So let's see. And now here,
So Fabio Sterpone, who is since 2010 CNRS researcher at Institut de Biologie Physico-Chimique in Paris. So he studied in Texas University at Austin, right? Well, I say something. And today he's going to talk about multi-scale, multi-physics environment to study protein in cellular environment. Sorry, thank you.
Okay. Is starting? Okay, can you hear me? It's fine. Okay, so thank you so much to the organizer for the invitation. I'm very happy to be here and share with you what we are doing in my group in Paris. Laboratoire de Biochimie Théorique is a CNRS unit at the Institut de Biologie Physico-Chimie in Paris. I will try to discuss about multiscaling, but with the perspective a little bit different from this morning, is the perspective of molecular simulation. So we will change a little bit the pertinent time and length scale of our problem. And what we are interested in is actually try to characterize the life of a protein in cellular environment. And this is what intrigued us, the fact that, and you know better than me, that the intracellular space is a very crowded environment with up to 30% of the volume that is occupied by macromolecules, protein of different size, shape, charges, DNA, RNA. And this crowded environment is now accepted to influence two aspects of the life of a protein. From one side, the transport aspect, and the other side is stability. So in some sense, crowding affects all the functional aspects that relate to this issue. For example, in reaction diffusion model, where a substrate needs to encounter an enzyme, the diffusion plays a very important role. And at the same time, the crowding space impact the large conformational change that are pertinent, for example, for the activity of molecular motors. Okay? So right now we have a lot of new experimental techniques that allow to explore the life of protein in vivo, but in some sense they lack a microscopic resolution. And mimicking what happened before in the field of structural biology, when computer simulation, molecular computer simulation, really support experiment to understand the behavior of protein, these experiments are called for the development of algorithm and methodology to try to support and provide the microscopic interpretation. I would like to, this is sort of conceptual outline of what we are going to discuss. I will use two examples to try to see how multiscaling is important. And The first problem that I want to address is the problem of aggregation. In particular, the aggregation that is important for neurological disease like Alzheimer. What is the important aspect here is that while experiments are able to track the presence of the fibril that are highly structured motifs that are considered to play a very important role in killing the neural activity in the disease, we do not know much about the early step of the aggregation process where misfolded or highly disordered proteins get together, stick together, aggregate, and eventually form this highly structured structure. The open question relates to the fact if the early step is driven by the formation of highly structured oligomers that represent elementary building block that then assemble all together to create the structure fibril, or on the contrary, if the aggregation occurs via a two-step mechanism, where the protein come together in a sort of amorphous phase with the disordered object that then coagulate together, and then there is a structural reorganization to create the fibril. And the second aspect is also the fact that in order to explain very well this kind of kinetics where we have a lag phase and then the growth and the elongation of the fibril, has been proposed, theoretically speaking, a sort of a catalytic role of pre-existence structure that act like seeds and allow to nucleate secondary fibrils. And I will try to show how molecular simulation can try to shed light on this aspect. The second aspect relates to stability in crowded environment. When we have a crowded environment, the target problem is subject to a different packing. And from the thermodynamic point of view, at the very beginning, the effect of crowding on stability has been rationalized with a simple excluded volume effect that basically is an entropic contribution that tend to stabilize the protein. Why? Because the protein to unfold need to stretch apart. And if we have a reduced volume, this excluded volume has a sort of confinement effect. So we predict always stabilization. But that's not the case when we have data from experiment, because depending on the crowder, the kind of, if it's a polymer or a protein of different charge or size, we can have even destabilization. And that's important to focus the fact that we can have a very specific interaction that can counterbalance this excluded volume picture. Before entering in the specific result, I would like to discuss a little bit of methodology. So when we, from the molecular point of view, maybe is annoying this part, is a sort of historical background. From the point of view of molecular simulation, the queen of the technique is atomistic molecular dynamics, right? Molecular dynamics is basically the solution of classical equation of motion. Once it's provide an atomistic model for the protein, including the solvent in most of the case, and provide a full set of parameters that we call force field, generally deduced or reconstructed by ab initio calculation, so with quantum mechanics. And this is a sort of timeline of the success of this technique. From the early simulation that has been carried out in the Harvard University by the group of Martyr Karplus, where a first protein was simulated for 9 picoseconds in vacuum, till to nowadays, when the group of DSO, for instance, was able to demonstrate that the folding problem is computationally solvable. Okay? And this timeline of success is associated to algorithmic development, for instance, how to treat well and efficiently long-range interaction with a good scale with the size of the system, and technological evolution. For example, a breakthrough is the development of the paradigm of parallel computing that has been very milestone in this timeline of success. And today we can mention the use of graphic cards that are really exploding and boosting the performance of molecular simulation, and even the design of specialized computer. This is the case, if you are interested in the story of the DSO group that designed a computer, the Anton machine, to provide and do very efficiently a kind of operation that are very frequently done in MD. The problem is that this story is confined to 1, 2, 3 protein in solution or in a membrane. So it's not actually the technique that can be used nowadays to study crowded environments. So one of the approaches is to try to use a smarter simplification that is coarse graining. Now, in particular, implicit solvent coarse grain. Because even if we are in a crowded environment, solvent water is still 60% of the degree of freedom. And we want to remove this because it's let's say, a waste of time. At the same level of the solute point of view, we can also try to coarse grain. Don't rely on atomistic description because sometimes we need a sort of grained representation that is efficient enough. And I will spend a few words later on. Now I want to focus on the problem to discharge a solvent, because in the exact moment where we remove the solvent, we are doing two bad things to the system. The first thing is thermodynamics, because we remove all the solvation effect. Now, if the coarse grain, or we are very good in coarse grain, or we are lucky enough, this kind of effect, thermodynamics, can be incorporated in the Hamiltonian. Okay? This is example, for example, when we mimic the behavior of hydrophobic particles that get together. Basically, even in implicit solvent, we are able to do this. Basically, we transport an entropic effect of the solvent to the Hamiltonian and enthalpic effect of the model. But what is really difficult to do is to model the solvent-mediated correlation. And when we are, or hydrodynamics in another language, because when we are in a crowded environment, we have protein that moving and they create flow in the solution, and there is a many-body effect that correlated this motion. How we can account it? Well, long time ago, Hermann and McCammon has provided a solution, algorithmic solution, that is the Brownian dynamics with hydrodynamics. So basically, this correlation effect is included in a tensor. But when we say tensor from the computational point of view, we say very expensive things, okay? And actually, a sort of resurrection of this technique occurs only recently, when the computer power is good enough. There are also some approximation, like infrared approximation, that are being used. And this technique has been somehow resurrected to study things like the search of a protein of binding site in DNA, or to explore the diffusion in solution, or the aggregation of lipids. A second technique that is more has been used in mesoscopic in the study of mesoscopic dynamics, has been developed by Ray Capral, is the so-called multiple particle collision. An alternative is where we are active. Is another strategy, is to combine something that comes from the world of particle-based simulation, that is molecular dynamics, with the technique that comes from fluidodynamics, that is the lattice-Boltzmann. These techniques has been originally developed in the context of polymer physics. Let's say that we are maybe among the first to try to apply this to biomolecules, where basically the length scale of the coupling between these two worlds is a little bit different. So lattice-Boltzmann MD in short. So we have two words. One word that is basically particle-based, in our context is a protein, for example, that can be described by an implicit coarse-grain model. In our case, we have our own coarse-grain model that we develop in the lab. And the solvent is reduced to its kinetic effect. Basically, we have virtual particle, and the solvent is described like a fluid, a field of velocity of discrete displacement. It's interesting to note that the solute is based conceptually on a discretization of the space. It's a Democritian idea, because we have particles, and live in the continuum. On the contrary, we have a continuum representation of the fluid that live on a very discrete space, because we need to solve it on the grid, this dynamic. And the two physics that enter in the game are, okay, classical dynamics for the particle, Fe equal ma, and the other case for the fluid is basically the Boltzmann equation with the spatial closure that is described by the collision. We use a simple operator, the BGK, that allow anyhow to reconstruct the Navier-Stokes equation in the limits. And we have a coupling, and this maybe is the most intriguing and problematic part, that couple these two words. And it's based on an ansatz, in the sense that the particle feel the effect of the fluid via a drag force. Okay, so difference in velocity with the coefficient gamma. Now at the macroscopic level, this gamma relates to viscosity. But we cannot do this assumption at microscopic level where the coupling is used. So gamma basically is a sort of free parameter of the model that we can tune. In particular, we have a rule. We tune it in order to have the diffusivity of the system in the dilute condition that match the experiment. Okay? So the lattice Boltzmann D is intrinsically, let's say, multiscale. First of all, because the time integration of the lattice Boltzmann, so the fluid motion and the particle motion, can be synchronous or asynchronous, depending on what we are interested in. Second, even at the molecular dynamics level, the particle dynamics can be separate the integration of different resolution depending on intra and inter force. This is a typical solution that has been largely used in atomistic and second, the fluid, the resolution that we can use to solve the fluidodynamics can be changed. And we can gain computational time because at a low resolution, the computational effort will be minor. And we can also incorporate this dual representation in a system. Imagine that there is a part of the fluid that is far away from the solvent. We don't need a very fine grid to solve its dynamics, because the coupling of the fluid with the particle will occur only in a specific region of the space. And then we can play the multiscale also at the level of the particle. Here, for example, we can use a flexible coarse-grained model with a particle that move according to some degree of freedom. But if we are not interested in conformational change, you can even reduce the representation with an elastic network, or reduce a protein to some kind of bead if we are interested just to some domain motion. Okay, with this in hands, the second ingredient is to design a coarse-grained model. Here, in very short, is what we have done in our lab. We developed a coarse-grained model that is called OPEP. What is the good and the bad aspect of this model? The good things is that it's a full flexible and is able to fold the protein. Okay? So that means that we can describe the motion of a protein with great accuracy. The bad things is that this is rely on a very fine description of the backbone of the protein, where we basically have an atomistic resolution. And this implies that we need to use a very small time step for the integration of the motion. Conceptually speaking, this model has been developed using several techniques. There are several versions, so it's a sort of stratification, it's an evolution of the model. The first model was obtained, the first set of parameters were using genetic algorithm, and the idea was, let's generate an ensemble of data representing folded, misfolded, unfolded structure of protein. And let's optimize the set of parameters in order to minimize the energy for the folded state, have a sort of good representation of the hierarchy of energy. And then we have refined the model using empirical data, in particular protein data bank, where we know that we can extract information about how some residue pack together. And then in order to account for some specific electrostatic interaction, we can use something rigorous like Boltzmann inversion to construct effective potential of mean force that guide the interaction of some specific site. So the model is not bad. We can fold the protein and explore structure that has been then verified experimentally, in particular the presence of beta barrel in amyloid aggregates. we can somehow reproduce the good difference in thermal stability between proteins. In nature, you know, you have a mesophilic and thermophilic organism that thrive in different environmental conditions. Thermophilic proteins are much more stable, and we are able to verify that the melting temperature of this object is different. So we have mesophilic protein that unfold at lower temperature and thermophilic at higher temperature. Please.
Just how you introduce the temperature here for 1
The temperature is controlling the temperature is controlling the dynamics, right?
No. How to introduce? You mean just introduce mobility or fluctuation?
Yeah, of course. It's a full molecular dynamics where we have degree of freedom that describe bond, angle, and dihedral fluctuation, plus we have a non-bonding interaction between the side chain and all the other particles. So basically, molecular dynamics is the solution of the equation of motion, where you have a conservative force plus a thermostat that allow the system to sample the canonical ensemble, and via the rescaling the velocity with good scheme, we have a definition of molecular definition of the temperature.
Okay.
Okay, and also from the mechanical point of view, the model is not so bad. There are some experiments where you can take protein and you can pull apart, like applying a force. We can do the same things in simulation. We can do with all atom model, and we can do with coarse grain model. Of course, there is a difference. But when you extract, for example, the delta free energy of the barrier separating folded and unfolded state, we are not so far off. Okay, so given a coarse grain, we are more or less satisfied. Okay, the technique has been used to explore different things. For example, the amyloid aggregation. Since we have a very good representation of the fluid, we can also explore exotic behavior like the unfolding or aggregation of protein under shear condition. There are proteins that in physiological condition work under shear. For example, the catch bond or the von Willebrand factor that are activated by the change in the shear flow of the urinary tract or the blood flow. And we have also started to use it to explore crowded environment. The technique is also, from the computational point of view, quite performant. This was the first time that we get out. It was we participated to the Gordon Bell Prize in 2013, and we just to demonstrate that the method was good enough. We simulate a system of 18,000 proteins. That is not small. It's a big system. Of course, at that time, for that particular context, we could use 18,000 GPU. Okay, it's not something that you do in the daily life, but was quite good in scaling. And the data we obtained, for example, for the diffusivity, match very well with the experimental data. Experimental are the red one, and the simulation are the yellow one. Okay, and recently we have also implemented a model for membrane. So we are somehow trying to play with the confinement environment and modeling sort of cellular compartment, and to study, for example, reactivity in this kind of confinement where we have substrate, Crowder, enzyme, substrate, and Crowder. This is a technique that we use to sample larger systems. Sometimes, however, we need to go back in resolution because we want to extract thermodynamic data. And for this, we need, first of all, to go back to an atomistic description. And we need to use a Nansen sampling approach to extract a meaningful thermodynamic quantity, particular free energy. I will be short on this, but let's say that one of the most used technique is the replica change molecular dynamics. The philosophy is we take the same system, we make several replica. Each replica is simulated at different temperature, so that the replica at higher temperature have a higher probability to pass a barrier and explore higher, larger portion of free energy landscape. And then we implement a Markovian exchange between the replica in order to sample at each temperature the free energy landscape. Unfortunately, this technique, since the exchange between replica depend on the overlap of the energy, and the energy scale, as the square root of the number of degree of freedom, the overlap for larger system is smaller and smaller. So you need many, many replica to achieve a good exchange rate in the Markovian sense. And so this technique is very limited to small systems. There is an alternative that is called REST2. I will go quick, but it's interesting because the idea is we don't scale the temperature. Let's use the corresponding state principle. Instead of scaling the temperature in the system, let's modify the potential energy scale. In some sense, if we scale the Hamiltonian, it's exactly the same things. What is the trick? The trick is that we can decide to scale in a different way the degree of freedom of the system. Here I just represent with pp the interaction of a particle belonging to the protein. PW is the interaction between the particle and the solvent, and WW is the interaction between the solvent and the solvent. And I can decide different scheme to scale it. So basically, I reduce the number of degree of freedom that are affected by the scaling. Basically, I kill off all the degree of freedom of the solvent, and basically I can simulate a larger system, have a small number of replica to achieve a very good exchange rate, and then sample very well the free energy landscape. There is a but. Within this scheme, the statistical mechanics is rigorous only at the reference temperature when we don't have the perturbation. But we have demonstrated that in a physical range of temperature between 300 and 400 degrees, the approximation for protein solution is good enough. At least when we compare objects of different stability, we are able to reproduce this stability shift between protein. Okay, with this in hand, let's start to discuss a little bit of some result. I don't know, I think I have still 20 minutes. Okay, so right now we can show some result. The first problem is, as I mentioned, is the problem of amyloid aggregation. This is just a picture to summarize the problem. Here we have in the neuron, in the membrane, we have the APP protein that when is cut in a bad way, start to aggregate. And this aggregation creates fibrils nearby the neuron. From fibril that are highly structural motif, oligomer can detach and then can reduce the activity of the neuron. Okay? We don't know exactly how we move from the disorder fragment A beta 142 and A beta 140 to this structure, as I mentioned. And basically the problem that we are facing is the following one. Generally, when we describe protein, we have this picture of funneling. We start from a random coil in order to find the folded configuration. In amyloid aggregation, basically, we go in a different way. We have misfolded structure that start to create create protofibril, and then structure fibrils, and then tangle in the nearby the neuron. And what we are interested in is what happened here in this region. So how we get to the isolate peptide to something that is highly structured. Here I start to present a result. First of all, I want to convince you that including hydrodynamics, even if it's from the computational point of view, cost is useful. I compare for a smaller system where we simulate the aggregation process of a smaller representative A beta peptide. Molecular simulation including hydrodynamics here and without hydrodynamics is standard Langevin dynamics. And in yellow and in blue, we indicate the size of the larger cluster that get formed during the simulation. So you can see that when we include hydrodynamics, first of all, the system aggregate first, so the kinetics is accelerate. And second, the fluctuation of this aggregate is very different with respect to the non-inclusion of hydrodynamics. Okay? When the aggregate form, the solvent, the coupling with the solvent help a monomer to detach and to aggregate again. So we have a sort of extra force that animate this aggregate. And by size fluctuation, we have a many-body effect because these objects fluctuate. So create a wave in the fluid that alter again the aggregation of other objects in space. And this is basically the picture that we have. We start to form aggregate, and this we have the isokinetic surface of the fluid. And what is interesting that if we look at two aggregates separate in space, we have streamline that connect the two objects. It's a sort of, if you have seen the movie Nemo, when the turtle flow in the South Stream Australia flow, it's something like this. We have peptides that are, however, driven together in a current way, but streamlined inside the solution. We have performed a huge simulation. This is, if you are not familiar, maybe I can try to give a number. This is a simulation containing 1,000 peptides with a concentration of 60 millimolar. So it's highly concentrated, but is what we can do in order to observe the aggregation process. If we transpose this system to atomistic detail, it would count 2.7 million of atoms. That is not something that can be done easily in atomistic resolution. So this is the power of the method. And it allows us to explore basically the aggregation process at the
just to get a basis of my field. What are the computation times if you do it on an atomistic scale and with your approximation? Just
so depend a lot. So let's say that for so a system of a few hundred K of atoms, generally we should use around between 100 and 200 cores. And depending on the power of the core and the code, we are in the order of a few tenths of nanosecond per day. Okay? Few tenths of nanosecond per day. So that's, okay? So if you want to arrive to microsecond, you have many, many days, okay, to perform. But just to
the hydrodynamics, I actually didn't understand your point that hydrodynamics accelerates the aggregation. Can you maybe explain that again?
So this
like
is what we observe.
Is the flow created by what?
By the movement of the particle.
Sure, but so is this no? Of course, but
okay.
Is this like a centripetal flow directed towards the aggregates because the monomers are somehow diffusing towards it, or what is it?
So the first things to consider is that when, with respect to a solvent-free simulation and a simulation with hydrodynamics, we verify that the diffusion coefficient of the particle is higher. Okay, is the hydrodynamics enhance the diffusivity of the single particle? First ingredient. The second ingredient that we verify is that, so we can try to explain this acceleration just by the fact that diffusion coefficient is more or less 30% higher.
Higher than what?
Sorry?
Higher than what?
So the philosophy is, if we take a dilute condition, you fix gamma in order to have the experimental diffusion of your monomer. Okay? Then you put the system in the presence of the other object, and with the same gamma, with the presence of hydrodynamics or without hydrodynamics, you verify that the diffusion coefficient of the monomeric species at the very beginning of the simulation is higher with hydrodynamics.
And the intuition is because of turbulence? Or?
Well, I don't say that we are in turbulent regime. It's a many-body effect that enhance the motion of the particle.
Sorry. What I'm interested in, let's say, is to try to understand the physics. So it's not really comparing without and with hydrodynamic interaction, but rather to understand, is there a coherent flow created by monomer diffusion? And for instance, I have a simple question. So if you increase the viscosity of a medium, like a real physical sample, you increase the viscosity, are you going to fall faster or slower?
I have to test. Honestly, I have to test. I don't know.
Okay.
I would say in the very the first step, I would say that is at the very beginning is slowing down.
to slow down the diffusion.
Yeah,
Right?
in my
So
opinion,
this is not a collective effect, it's a single particle effect.
at the very beginning, yes, but then you have a second phase, because here, if I time it, I can go to the other slide, because we have several regimes in this aggregation process, okay? When the monomers start to get together is this very initial regime. And I agree with you, in this part, basically everything is controlled by, I think, the diffusion of the monomers, okay? But there is a second regime is here, where we find that the growth of the cluster is discontinuous. Why is discontinuous? Because basically we have four aggregates of a given size, and this object comes together, okay? They fuse together. At this point, the size fluctuation of this aggregate enter in the game, okay? And so these also create a collective effect in the solution, because we have
Right, but this coalescence of aggregates together, this also exists without hydrodynamic interaction.
yeah, but it's very reduced, right?
Yes.
Is very reduced. The jump, so imagine that here at the jump, they occur later, and the fluctuation of this size is the fluctuation of the size of the aggregate is smaller. So this make me think that there is something adding at a given moment. It's a sort of, let me abuse a terminology. It's like the aggregate behaves like an active particle.
Well, that's why I was trying to understand.
I don't know if it's correct. I have no proof on this.
What is the different coefficient dependence with size in your?
So I have not the data with me. We see that at the very big is not a simple 1/m.
No, of course, with some. I mean, the sum and then we would say that the dependence is very small. It's logarithmic.
Yeah, exactly. Yeah, well, I don't know. I need to check. I remember I plot the data, but I have not the correct scaling in my head.
But in your situation, it's purely viscous flow in this, as far as I understand. So in principle, you should be.
I can extract it, of course, but the problem is that it's difficult to us to calculate a diffusion coefficient with an object that is a transient in time, because to converge, well, I can track a single monomer and try to see depending. Well, but the cluster changes size frequently. What I have done then, I have to check the data. I've taken the final cluster that obtained that are very different size, and I separate this object, and I simulate this individual cluster to try to see the dependency. But I have not the data, I have not the answer, honestly. So I anticipate some aspect of this plot. So basically we have a first regime where the monomer get together, then we have a discontinuous regime where this, let's say, aggregate, we will discuss later if they are structured or not, they start to fuse together. So we have this coagulation mechanism. Then we arrive at a regime where basically we have formed a very, very big cluster. The further kinetics became strongly diffused limited. So these objects that we have formed in the solution, as we will see, they are very big. So the time scale to try to fuse more, it's longer and longer. And we have to trick the simulation, as I will show. And what is interesting here is that this cluster also present a fragmentation event. So when we form this big object, we have some weakness that created this object, impose a separation and the diffusion of the larger cluster. To make everything easier from the visual point of view, this is the larger object that we create. There is a very weak region here, and the thermal fluctuation and solvent fluctuation help the system to separate and refuse, separate and refuse. So this is a sort of nice evidence to the fact that when you create a larger object, then you can start to fragment, and you can free in the solution probably oligomer of a smaller size that can become the toxic species in the amyloid content. Also, I want to stress here the creation of a pore. Why I want to stress here the creation of a pore? Because the fact that amyloid can form pore is considered a very pathological off-pathway aggregate, because this pore can enter in the membrane and can alter via the flux of the calcium ion the equilibrium of the difference potential inside the cell. Okay, I will try to go a little bit faster, but this is again a characterization of the first part of the aggregation where the monomers get together. And what I want to stress here is a structural motif. These are beta, is the percentage of amino acids that take beta structure in the aggregate. Okay, so having in mind that the fibril are highly structural object with a high contact of beta structure, we see that immediately after the simulation starts, so when the monomers get together, they start to take beta configuration. So when they get together, they start to explore a part of the configurational space that otherwise the monomeric species is not present. So the percentage of beta structure boosts, but then increase very, very slowly. That means that the mechanism that we observe is the creation of partially disordered aggregate that then fuse together, and when the size of this object increase, the further conversion of the peptide toward a beta structure is slowed and slowed and slowed down depending on the environment and the local packing. This is another way to study the monomeric diffusion, but what is important here is to show the mechanism of the coagulation, of the fusion. I insist here because probably it's the first time that this kind of picture is generated in silico. So generally people believe that the elongation is a sort of capping process. You have an aggregate, then object start to cap and elongate this object from head to tail mechanism. What we see is that actually we have a variety of mechanisms. We have offshore, for sure we have head-tail mechanism, but we have also branching mechanism. Remember what I said at the very introduction, that sometimes the lateral branching considered as a possible alternative pathway in the aggregation that can help to understand the kinetics of the aggregation process. And we have also bridging mechanism where we have aggregate and smaller ones that get together and help to fuse larger and larger objects. This is again a vision of the pore, just to highlight the fact that this object can be present in the fibril. People has always believed that the pore can get only as a separate structure in the membrane. We show that this is possible even in solution. Question is how this object then separate or enter in membrane, or even if it can be used to capture object ions in the external cellular space.
I missed the property that you put of the elementary monomer. What is the property of the elementary monomer that you...
The input. Yeah. The only things I tuned the gamma the diffusion is the only ingredient.
The aggregation is just isotropic. The aggregation when two.
Well, the monomer is a specific sequence. Okay, the sequence is basically this fragment that we use is the hydrophobic core of the protein. Each residue is on specificity, so is not isotropic.
Okay. So what is okay? But I suppose this is not very well known. I mean, the interaction of the different residues.
Of course, is actually people don't know very well what's happened. Well, the force field is a transferable object that has been built for general peptide. So we don't specialize this for amyloid.
If you change a little bit the property, it will change.
No, a little bit, I won't say that will change much. Of course, if I unbalance completely the hydrophilic versus the hydrophobic interaction, I will enter in a different world.
Or in other words, could you simplify a little bit this...
the monomeric interaction? to accelerate. Well, the important things to have a high resolution is because we want to see the acquisition of secondary structure. So we need some degree of resolution that must be present. Okay, but you are perfectly right that we can simplify to further see the situation, because actually this is the end of the simulation, right? We have a huge aggregate of 600 monomers, and then we have 3 other objects of 100 monomers. And we start to see that there are islands of structuring elements, more or less random distributed in the aggregates. Now the question is, can we further aggregate this object? In this resolution, the answer is not. So we decide to, this is the game that we want to do, to reduce the resolution. We can model each of these objects as an elastic network. We reduce the degree of freedom because we don't want to see the dynamics of the monomer inside the aggregates, but we want just to see the aggregates, how they fuse together. At this level, we can alter the mechanics because we can use a larger time scale. We can use a scaling argument in order to preserve the kinetics of the system, because we increase the time scale. We can, let's say, use a larger mesh for the lattice Boltzmann. So we need to use some scaling argument to alter the kinematic viscosity in order to preserve the kinetics of the system. And then we can try to see what's happened. So we can go in a faster way, have an extra microsecond, and what we see is this lateral branching become real. So the object, when aggregate, create this branched structure. This is an open point. In my opinion, I have the feeling that is a sort of entropic catcher. So the fact that we have some lateral branching may help in the further aggregation of object, because it's like an antenna. Okay, and then maybe it's a template that this object can get separate and become a sort of way to grow the fibrils.
This branching is random. I guess it can happen anywhere.
Anywhere. Well, what I'm doing right now is try to understand if there is some peculiarity in the surface where these objects get together, if it's more hydrophobic, as I suppose, or there are some specific role of ion pairing that are present in the object. But these are very fresh results. So
it seems that if you want to make large-scale structure aggregates, branching would be complicate this. Like leads to very diluted aggregates, a lot of branches.
Sorry, if I want to have...
But if at the end of the day you expect to have very structured large-scale aggregates, as you showed in the first
in the ideal picture of the final fibril. I think here we are in a sort of pre-fibril state, right? Where we have these objects that start to aggregate, maybe these can fragment and became a template. And then we have another time scale that is the full reorganization of the peptide inside this object toward a beta strand. It became a problem of reaction diffusion in the free energy landscape of the peptide, because we have to overcome barrier to switch hydrogen bond pattern and to form a beta structure. And apparently is a sort of a separate time scale. Okay, so I don't think I have time to enter in the...
There are still 10 minutes.
10 minutes? Okay, I want to show something else. It's another way to play with the scale. This is another problem. It's still related to aggregation. There is, problem, amyotrophic lateral sclerosis, a very bad disease. And SOD1 is the protein that is considered key for this disease, because some mutation, SOD1 is a dimer, and when some mutation occurs, this protein became monomer. Becoming monomer, it became less stable in solution. And became less stable in solution is highly probable to misfold and to aggregate. Okay? And we have our experimental collaborator, Simone, they use single molecule measurement to probe the effect of of crowding on the stability of a construct of the protein that is a monomer, and the effect on the mutation. So the collaboration was based on the idea that our machinery can be used to explore the behavior of SOD1 in this cell-like condition. And this is what we have done. We have taken SOD1, put on a crowded solution that mimic the experimental condition. The crowder is the large BSA protein. Let me say another thing. What they think is that one of the key region that characterize the interaction of SOD1 with BSA or other macromolecule in the crowded environment is the region. Let's call loop 7, okay, just to fix in mind. So for us, it was important to understand if we can use the machinery to explore the packing environment of this SOD1, okay, in BSA. We have performed this simulation. We have a lot of crowder, some target SOD1 protein. Simulation extends to 1 microsecond. We were able to explore different local packing. And this is sort of configurational clustering that we can do to individuate how SOD1 interact with BSA. And we have basically two family of packing. One that we consider one-to-one. SOD1 interact with just one BSA. And the other condition is where SOD1 form a sort of sandwich with two BSA. Okay? Now the game that we did it is, okay, let's try to change the resolution. But this time not reduce the resolution. Let's increase the resolution because we want to acquire some molecular detail. So we extract the characteristic packing and we backmap this to atomistic resolution. We have a full procedure to try to how to backmap a system that has less resolution, so less degree of freedom, to a system where we have a full atomistic description. And then we can end up with these systems that are very big in size, of SOD1 in solution, SOD1 with one BSA packing, SOD1 with two BSA packing, and we can try to extract information. Try to see how the loop 1 change when interact with BSA. We verify that can take some two kind of conformation, extended or compact, depending if the SOD1 lie down on the surface of BSA or if it's quite orthogonal. But what is interesting and more important is that we can try to reconstruct the stability curve. What is a stability curve? Is to measure the fraction of folded and unfolded state as a function of temperature for the dilute condition and the effect in the crowded condition. And what we see is interesting because the experiment tells us that basically they expect a very weak effect of this crowding. That is very strong crowding because 200 milligram per milliliter, okay, is a strong packing. But as you can see, the melting temperature of the system is not really affected by the presence of the crowding. So what we demonstrate too strong. Let's say that what this data suggests is that this simple excluded volume picture that predicts stabilization does not apply, and that the specific interaction between the protein and the crowder weaken this contribution in order to have a melting that is comparable. This we skip. This is just perspective. What we are trying to do right now is to moving on. I described before the idea to study the reaction kinetics in confined space. In collaboration with David Altman, there is the idea to use lattice-Boltzmann coupled to PNP in order to study the electron diffusion inside the neuron and maybe the effect of Crowder on this electron diffusion, and then use a multiscale on-the-fly representation to describe vesicle fusion during the trafficking in the Golgi, changing resolution from something that can be fully fluid or a mixed fluid particle representation. This is acknowledgement of all the people that has worked with me. This work is done in tight collaboration with Simone Melchionna in Rome, that unfortunately was not here today, and Philippe Deremont. These are my students, and I thank you for the attention.
Okay, are there questions here?
I have a question. When you were showing the initial stages of the aggregation, and that you had a large cluster and then a set of smaller clusters, and my question was if you have good data on the distribution of the sizes of the small clusters. And the reason I'm asking is that there are simple statistical physics models of aggregation with chipping, where as a steady state you will get an infinite cluster plus a power law distributed tail of small clusters. I'm just wondering if there could be a relation to your
It's
data.
probably this that you are asking for.
Yes. Like the distribution of sizes. Is it? Does it look exponential? Or would it be a power law?
Well, the problem is that I guess is a sort of a power law. So let's see that. Let me explain. This is the probability distribution of the size of all the oligomers, the cluster of a finite solution for time window. Okay. So 10 nanoseconds, 20 nanoseconds, 40 nanoseconds, 60 nanoseconds, 8 nanoseconds. So at the very beginning you have a distribution that is centered around the monomer state and few dimer, trimer, tetramer, whatever, and then you start to have the tail. So you start to populate larger and larger cluster. Now, probably we can try to fit with a power law. Is not yet converged because we know that the system, when we end this analysis, is not fully aggregate. For sure, what we can see here is the arrow. We start to see a bump in the distribution. The resolution is not good, but you start to have a bump. That means that you have a sort of critical nuclei, or a critical size of the nuclei that start to form, and these maybe are in the simply polymerization model that are used is the critical size that is required to fuse together this oligomer and to trigger the aggregation.
Is the bump moving with time?
Sorry?
Is the bump moving with time?
A little bit. You see, there is a first bump, and then is over there is around a size that is between 10 to 20 oligomers. And what you see also here is a transition matrix. So at the very beginning, basically, this is the axis. Now this is the size. Okay, starting monomer with respect to final monomer. Starting cluster size, final and cluster size. That means I can follow with a sort of graining what is the probability of a monomer of a peptide to stay a time t in a cluster of size n, and to end up after a while in a cluster of size m, right? So it tells me how what are the elementary mechanisms that allow the object to grow. And basically at the very beginning we have +1, -1, okay? Basically it's just the addition of one monomer at time. But when times pass, we still have the leading process is the inclusion of a monomer, but we start to have, a very important contribution from the inclusion of higher objects, dimer, trimer, pentamer, and temer. So that means that we enter in this regime of the coagulation mechanism.
Yeah, you mentioned in on the last slide that you wanted to go into the fusion of vesicles. Could you shortly explain where already your method, you are thinking the methods that you have so far help you with doing that, or where you're seeing still some gaps, where you see limitations of your current approach?
So, but I can explain. So the current implementation right now allow to describe, let's say, a vesicle in a very detailed particle level resolution. Now, if I want to have vesicle transport like in Golgi, I cannot handle in this way. So I need to have another representation. There are nice models, for example, that use triangulation to describe a sort of a membrane as a sort of elastic object. This can be sort of easily implemented in the code, in the structure of the code, and try to see how this object can flow. This still is particle and fluid. Another approach can be to describe the fluid in order to mimic a membrane. So have two species of fluid. One is the solvent, and another is an object that is more or less a vesicle, that is constrained by some internal harmonic restraint. And then my idea, so I discussed, it's open discussion, is to have this representation, and when these objects come together, for example, have a sort of switch of representation in the critical part, and to increase the resolution where the object tend to fuse, sort of having a molecular representation of the fusion of the membrane. So this is my dream, but it's not on the real axis for the moment.
What exactly you mean? You have just water, or is it you have a lot of ions there as well, interactions, or
what I show now is just water. A priori, lattice Boltzmann can handle different species of fluid, including ionic species that are not punctual. They are described like charged species that flow in another bath solvent, so it's doable. And you can also have biphasic behavior. So the technology is, and the formalism is quite robust on this.
Can imagine that his behavior changes if you have ionic forces there in the solvent.
In the aggregation?
For example, this, or if you have, electrostatic forces, this.
Well, electrostatic, the question is how the screening is strong.
Yeah, it depends on the concentration.
For sure, I can share with you a typical molecular example where, for sure, I know that the presence and the charge species can completely mess up the situation. And there are experimental. If you Google the aggregation propensity of lysozyme and the formation of cluster, you realize that any kind of molecular simulation that cannot reproduce the strange behavior of lysozyme when they aggregate, because probably there is electrostatic steering or some strange screening effect, because lysozyme is quite charged. And basically, when you increase the crowding, you go completely out of a sort of microviscosity scaling that is sort of proportional to the fact that you form a cluster of a larger size, so you increase the microviscosity of an environment. And this lysozyme maybe is a typical example of what you say, that including the electrostatic and the many-body electrostatic effect is probably very important in some cases.
Are there other questions? So just I had just a small one, so it's related to Jorgen's question. So if the solution is composed of ions, so the electrical field can be modeled with the first algorithm, right? However, if now we have a protein that is charged, so could we model it with this algorithm?
Well, when you include ionic species, of course you have to add a layer in the solution of the dynamics that account to electrostatic. Okay, so a solution of the Poisson equation in some sense. And there are parameters, of course, that you have to include, like the screening, the electric constant. So you have to prepare the solution of the electrostatic problem.
Okay.
Okay.
I think we can applaud the speaker. So now we have 15 minutes of coffee break. So the second and the last speaker of this afternoon. So Andreas Hellander, who is an associate professor at Uppsala University, and I'm going to talk about hybrid simulation, and I think I'll let the rest to him. Okay.
Yes, thank you. So I messed it up a little bit. I confused it to you guys because I accidentally changed the title on my slide. So sorry about that. But I think this one is a bit more accurate. So I want to talk to you today about what I call high fidelity single cell simulations. And maybe high fidelity is a bad word because we have seen certainly higher fidelity in this session than I will talk about today. But for me it's kind of about resolving intracellular gene regulatory network kinetic models on mesoscopic or microscopic levels. And I will sort of make this talk about leading up to sort of work on hybrid methods that we've been doing, trying to combine these different scales for more efficient simulation. So I'm an associate professor in scientific computing. I have a distant background in molecular biotechnology, but have drifted off a lot into methods development. So the talk will be largely about methods, I would say. So a little bit about me and my lab. So I have a group in Uppsala in what I just call it computational science and engineering group. So we do quite a lot of different things, but these are, just want to put here, this is our beautiful campus that we will sadly move from. So we have a lot of talented students and postdocs doing different things. So this is a little bit where we are from. So we do essentially we have sort of two main directions in the lab. So the first one is work I've been doing since I was a PhD student in computational systems biology. And as I said, a lot about multiscale methodology for cellular pathway simulations. An algorithm theory for direction diffusion kinetics, and this is what the topic of the talk today will be about mainly. And then at the end, if I have time, I also want to show you some work that we're doing that ties into this in something we call e-science tools and techniques. So I also see myself or my lab as an e-science group. So we do quite a bit of work these days on distributed computing, cloud computing, data, big data management, data stream processing, those type of topics. Something we call smart systems for computation-driven scientific discovery. That's a bit of an ambitious title, but it's essentially about trying to use these tools that we talk about here in this workshop for coming up with clever ways to interrogate biological systems in an autonomous fashion. So we'll come back a little bit to cloud computing and multicellular simulation at the end of the talk, so you bear with me if you have read that in the abstract. So essentially this talk then is, I'm going to start off making sort of an argument that I think a lot of us will agree to, that reduced models are good because they are fast, but they're not always simpler. It is something we often say, we reduce the model to make it simpler, but I will tell you what I mean with that. So I really like spatial stochastic models. That's sort of my favorite modeling framework, and I will try to sort of convince you that that's valid. Then I will spend a lot of time to talk about the relationship between two of these models, the direction diffusion master equation, which Stefan talked extensively about. And yeah, I adopted terminology from Samuel Isaacson. He calls this Smolchowski diffusion limited model. So it's essentially the model underlying GFRD simulations. So we have done a lot of work on looking at the relationship between these two models, trying to analyze that to see if we can understand them better. And then those results will sort of lead up to our latest work, which is a paper from last year on hybrid methodology, where we sort of blend these type of models together. So something that we have felt has been sorely missing is criteria to do this automatically, to partition systems and simulate them in a hybrid fashion without having to first understand the system in detail in order to make this partition. It becomes a bit backward. So this is like a priori criteria. And then this is work that has been done over many years in close collaboration with Stefan Hellander, which is the mathematician behind a lot of the work we do. And then at the end, I'm going to talk about, because we've seen a very nice talks today about sort of multicellular systems and simulation frameworks. So this is where it ties back into cloud computing a bit. We have, together with my student Adrian, started to come up with sort of a framework to put things together, put different simulators together to create cell-cell communication models. So there's not a new model there, it's a tool that will let you take models and put them together and simulate them. So this is a rough outline of what I wanted to talk to you about. So I hope I have time to cover all of it. So I wanted to go back to a model that we worked on back when I was a postdoc in 2013, and it was in the talk, the first talk in the morning. We actually saw some new simulation output from this model, which was nice. So this is a model which I use to sort of illustrate sometimes that a spatial model can be quite good, in the sense that you can make it very simple at the price of simulation expense to capture biological properties. So this is a model of something we call the HES1 gene regulatory network. And it's a classic example that has been used extensively in the, I guess, both biology literature, but I have the methods perspective here to demonstrate a negative feedback loop. So this is the sort of core network that we're interested in. So we have some, essentially a small negative feedback loop motif, where the HES1 protein represses its own transcription. And experimentally, in a very beautiful paper back from 2002, sort of we observed oscillatory dynamics in many different cell types, displayed by this network. And it has a key role in somatogenesis and linked to cancer. And it's a nice model in many ways because it's involved in a lot of processes. Also linked to differentiation responses in embryonic stem cells. So this is a system that shows a lot of variability. So when you observe the HES1, this was a really poor picture, but when you observe, can you see anything here? So these are time series output from this paper, this work here, where they observed HES1 in embryonic stem cells. And you can see that it's kind of like, it's hard even to say if it's oscillatory. Let's call it oscillatory behavior, but with a lot of noise. So it's highly variable expression of this protein, but it has some sort of cyclic structure. This picture is even harder to see, but here they have plotted sort of they ran these experiments for 80 cells, I think it says 80, and looked at the sort of mean period of the oscillations and saw that it sort of also varied quite a bit. And this was kind of used then to make this nice sort of relationship to heterogeneous differentiation response. Because what they observed was that if you have cells that have high HES1, when you transfer cells to differentiation medium, it goes to one type of cell. If you knock it out, it leads to less heterogeneity and vice versa. So that it's really sort of clear that the expression level of HES1 sort of drives the cell fate. What happens then if you observe a population of cells? You try to synchronize cells and then try to differentiate them. You sort of end up then with this mixture of cells anyway, because this cyclic periodic behavior, sort of this high level of noise leads to period drift. So you quickly have sort of oscillators out of sync in individual cells. But the main point was that sort of this this implicated Hess1 also into cell fate by suppressive noise signaling. So this kind of high level of noise here is important. This has been a favorite system for methods developers across over time, and a lot of models of this has sort of been proposed, starting from simple ODE models in that original experimental paper, where essentially, and this was a pure mathematical problem, they had to introduce sort of hidden unknown species in this model to observe oscillations. But that had to do with structure of ODEs, and then it's been modeled with delayed differential equations, well mixed stochastic delayed differential equations. So this was Kevin actually, he's not here sadly, but and then also up to PDEs then with a spatial model. So in each of these sort of model progressions, more and more, I would say, of the biological features were captured. So here, for example, you sort of, with the delayed differential equation, you could observe oscillatory behavior without introducing additional species into the model. Then with the stochastic delayed differential equation, you could also observe noise, but you could not observe so it had some kind of artifacts, for example, that you had a much higher output of mRNA than protein, which wasn't biologically reasonable or didn't agree with the observed data. And then PDE models, you could observe essentially the same thing, but not noise, but you don't have to have the delay. So you instead have the diffusion transport of molecules. So all these models rely on Hill kinetics. They have sort of Hill terms in the binding of Hess1 to the promoter. But something that when we started looking at this system as a model problem for our spatial tools, we didn't really like this because we couldn't find any real evidence for this type of cooperative binding in the literature. So we sort of felt that this was needed to observe the oscillatory dynamics of the experiment, but it was not supported mechanistically. And the same there, you can also see in these studies that you are very sensitive to these delay parameters. So we took our favorite spatial stochastic simulation tools and made a spatial stochastic model of this. And we said that, okay, this model should be bare bones. It should have no delays. So it should have diffusion transport, it should have import into the nucleus, and it should have binding mass action kinetics only. So we also said no Hill kinetics. But instead, we have this kind of high spatial resolution under the stochastic RDME model.
Could you just go one slide back again? The models, so the PD was that a delay PD or?
No, it was not a delay PD.
Okay.
It was not a delay PD.
Get the same with the PD exactly.
Sorry?
For the, what do you call it, the oscillatory.
Yeah.
Or the
Yeah, exactly. That was the point. You didn't need a delay in the PD, but you didn't have the noise on the other hand.
So your model, what's the difference again?
Yeah, so this was previous work. So what we did is that we took this system essentially and made a spatial stochastic model. So this is based on this reaction diffusion master equation formalism that we heard about today and also in Stefan's talk. So we have essentially a spatial stochastic model.
So the diffusion somehow also introduces delays.
Yeah, exactly.
The typical time scale that is induced by this diffusion, does it correspond to the time delay in the delay differential equation?
Presumably, I haven't studied the exact numbers, but that's the main idea, I guess.
Because I would consider the delay differential equation just as an approximation to the PD.
Yeah, exactly. Yeah. But what was also different here is that we said we should not have a Hill term because it wasn't so, yeah. Yeah, it could be that as well. Yeah. Yeah. So that's. Yeah. Yeah, I mean it's produced after some given time, an exponential time in the model. You could do it as a delay model. Yeah. So I'm not saying that delays are bad all the time. I mean they can be essential. The point being that this model doesn't really need that to display these oscillations. So by doing this, we are able then to quite, not only qualitatively, which previous models also succeeded doing, but also quantitatively with kinetic parameters that are in reasonable ranges. Some of them weren't determined experimentally, some of them were actually quite well determined, like the lifetime of mRNA. Those were actually measured with fairly high precision in previous literature. But here we can also capture quantitatively the behavior of the experiments down to distributions of period times over a cell population. So this we thought is kind of nice. This also allowed in the paper about this that we wrote. So we, for example, looked at if you introduce a drug that inhibits binding, for example, what happens? It allows us to ask questions that are more mechanistically oriented. Also by sweeping parameter space in a quite large regime over diffusion constants and these rate parameters, which we then can directly relate to binding events and so forth. We can also see that this kind of oscillatory dynamics, it's actually quite robust over parameter space. So you observe this type of oscillatory behavior for this network over a very wide range in parameter space, but whenever we see oscillations, we also see this very high level of noise. So the model here actually predicted then that this high level of noise and hence this kind of differentiation response that you observe experimentally can actually be attributed. We don't say that it is attributed, but it's supported by the model that this can actually be due to inherent noise. So this was kind of like a nice, but I think this talk is not about the HES1 model. I think what I wanted to make the point here is that I like these type of spatial models because by introducing the additional complexity of a more expensive simulation, of course, I also get a model that has parameters that are more directly related to biology, and actually that has at least hope to be directly measurable. It's hard to measure binding parameters. Yeah, so we didn't. So those were measured by others in experimental work, and others we didn't get. We just varied them over a wide range of parameters. So those are then like qualitative outputs. And then also in this, where I said it agrees quantitatively, then they were actually tuned to the data, this time series data that was observed. But that's of course an indirect way of inferring parameters. But this work was done with my favorite tool. It's the reaction diffusion master equation. We really like this model in Uppsala. There's no coincidence. Well, both me and Stefan come from the same professor that also like this model. So we grew up with this, but it's quite nice. It's quite nice because it's quite simple to implement. It's quite flexible. So work that we have done in the past in this Udemy software and theory behind that, working out how you can do this on quite general grids in complex geometries and so forth. We have the NSM algorithm, this is quite efficient. Now there is parallel tools. So there's a quite big ecosystem of tools that will let you do modeling with this framework. We have this assumption of point particles, which can be quite severe, of course. So we have to assume that, and we have to assume that reactions are well mixed between inside these kind of voxels. But I really like this tool because it's also extremely computationally efficient if the mesh size is chosen big enough. Unfortunately, it has become clear then in modeling literature that very high spatial resolution can actually also matter even for this type of kind of coarse-grained molecular network models. So this is a classic paper by Takahashi and Tenvolde, where it was published in PNAS in 2010, and it kind of like set forth a lot of work in methods development. So it's a model of a doubly phosphorylated map K cascade. So it's quite a generic motif. And the point of their sort of modeling work was that you really need, there are situations where you have if you have very rapid reactivation of the phosphatase there, I don't remember, I think it is this reaction. So this is just a traditional model of a distributed enzyme process. And then if you have a very high value of the K7 parameter there, if you want to go mathematically, you introduce the need of a very high spatial resolution. And this is due to the fact that, say that you have these proteins that come together and react, and then they dissociate. If there's a big probability of rebinding before this molecule has had time to move away and become well mixed, then you really need to capture this on a very high level. And what I think was very nice with this modeling work is that they also, I mean, in this type of model, this very detailed kinetics actually has quite large effects on a macroscopic scale. So it actually can change the behavior of the response of the pathway from distributed to processive, for example. And the point, of course, because they are the inventors of GFRD, so the point they made, or that they showed, was that you really need this high spatial resolution in order to, you have to resolve it on a particle-based simulation in order to actually capture this transition effect. And sadly, I mean, and this modeling framework that they use is then this Smoluchowski model simulated with their sort of invention, the Green's function reaction dynamics, where particles are not point particles, they're hard spheres, and reactions happen as a boundary condition on when spheres touch. So it's here, and here you have a binding rate for this binding rate between molecules Kr here, which is an important one in my talk. I call it the intrinsic microscopic reaction rate. So sadly, the RDME is not able to simulate this for very high levels of K7, which I will come back to. So I mean, coming back to this question then, so when do you need what type of model? So as we saw there, the RDME is very nice. It was very effective when we studied this S1 system, because those reactions weren't in a very diffusion limited regime, or actually I don't really know if they were, because this theory wasn't known when we did that work. But you have to rely on a large enough mesh. On microscopic models, on the other hand, I mean, they are able to capture, for example, these very fast rebinding events that Tenvold and Takahashi talked about. But they are extremely expensive if you have larger number of particles. So even this S1 system that has modest number of particles we have tried to simulate is extremely expensive with GFRD. So it's hard. Sadly, I think if you do a lot of modeling, you realize that most models that you encounter doesn't really fall into one single category, that you either have coarse mesh or that you can have a few very small amount of molecules. So that's a problem. So the point I wanted to make here as well, and this is a bit of a sort of scientific computing perspective, is that the choice of models should not be based on biological intuition or trial and error, because this is kind of like how modeling has been done in our field. That you try some model, you try RDME, you try GFRD, mold in different type of software, and you vary some parameters and you see if the result changes. And I mean, sure, that's a valid way of doing things, but I mean, we must strive for something better. So we started studying this relationship within these models, and what I wanted to say there is that there is no reason to think that the RDME should approximate the Smoluchowski model. I mean, they're not really, the RDME doesn't arise as a discretization of that model. But you can still ask sort of how they relate them to each other. And then we have this very classic work by Collins and Kimball that kind of relates the macroscopic or mesoscopic rate to this intrinsic microscopic parameter. So there's a known expression here. How do you pick a mesoscopic binding rate in the RDME or PD model? If you know the microscopic parameters here, they are the reaction radius, diffusion constant, and this intrinsic rate. And you also have this detailed balance condition which should hold. So this is kind of classic theory. Also is something, I think there was a question this morning about using SSA, and it has not been derived for the for solutions and that kind of stuff. But this was a problem also that was bugging Dan Gillespie quite a bit when I was a postdoc in Santa Barbara. So he also worked and sort of derived what he called diffusion or biomolecular propensity function, because he was worried that people were using SSA even though he hadn't really thought about this setting when he created the algorithm. But essentially you come up with the same rate there. So this thing is a good approximation. This connection holds if the mesh size or the reaction volume in some sense is much larger than the particle radius. This is not very useful as a numerical parameter or a numerical condition. It has to be much larger than. I mean, we want to be more precise. So the question really is here then, how well does the RDME approximate the Smoluchowski model on fine scales? We know that it does, that it can work in this setting. The sad answer is that it doesn't do it very well at all if you are naive. So there was a classical paper in our field by Samuel Isaacson that sort of showed that as you shrink the mesh in an RDME simulation, you kind of lose all the contributions of biomolecular reactions. So essentially, we call this the breakdown of the RDME. Essentially, what this is the breakdown of the point particle assumption. It doesn't really work, and it's a natural consequence of random walks on lattices, as we will see. About the same time, I mean, a lot of people study this. So Urban and Chapman, they show that you can sort of avoid this to some extent if you introduce scale-dependent reaction rates, mesoscopic reaction rates. So they did some derivations there based on Cartesian grids without sort of invoking the microscale model by saying that the steady-state densities should be invariant to mesh size. And the same time, also Johan Elf and David Fange did work on, and Otto Berg on spherical grids and obtained actually alternative rates in 2D and 3D. And they work well in their case if you have non-local reactions. You introduce reactions not only within your own voxel but with neighboring voxels. So essentially you have this picture that emerged about regimes of validity of my favorite simulation tool. And I like to draw this line here, again bad resolution, where as the mesh size shrinks, you have this regime where conventional RDME using Collins-Kimball's rate gives you good modeling results. Mesh sizes are large enough for it to be valid, and I mean they can't be too large, of course, because then you can't resolve diffusion. But then as you shrink the mesh, you try to improve, the resolution improves up to some point where it actually starts becoming worse. So this is the yellow region here, because you have this kind of loss of biomolecular reactions. And then H star I will come back to. So we will see that there is also this regime where there is no, where it sort of just diverges. As Urban and Chapman showed, I mean in this yellow regime you can do scale-dependent corrections. You might think, and I thought that for the longest time, that okay, but this is just mathematical theory, and it doesn't really matter. I mean, of course it will break down if you approach the molecular radius. Obviously, you should go to a hard sphere model. The problem is that the errors can actually be quite large, even for large meshes. So if you actually look at the approximation there, it's not a good approximation, even in the case where you maybe are 10 or 20 times, have a mesh size 10 or 20 times the molecular radius. if you compare to this microscopic model. So that should be very clear. Everything I say today assumes that this Smoluchowski model is the gold standard. I know that there are many other models, but in order to do some analysis, you have to sort of fix the models. So one result that we got in 2012, me and Stefan, was that we observed that there seemed to be this kind of fixed limit where you cannot correct the rate expression by introducing scale dependency. So we studied this problem by a very simple model problem. So we took a single irreversible reaction and then we took it to the limit of perfect diffusion control. Essentially we made the microscopic binding react infinitely fast. So the reaction is completely limited by two particles actually meeting each other. And then by sort of looking at you can easily observe then that the reaction time, so the average binding time, the average time until a reaction happens, this is the tau micro here, is then a combination of the average time until two molecules meet for the first time by diffusion, and then that average time until they, or the time until they react given that they meet. So if you write the binding time in this form, you can sort of quickly see that we know these individual parts on the microscopic scale. So this is, these expressions, we don't have to go into detail, but these were actually derived then by Otto Berg in this work here. But the point being, these two contributions are known on the microscopic scale, at least if the volume is large enough. Not the reaction volume, the actual, the total volume of the system. So this is V here. So this is known, and then if you do the same thing for the mesoscopic scale, so you look at the time until two molecules meet when they diffuse by hops on the grid in the RDME, and the time until they react when they find themselves in the same voxel. And this here is some actually work did by Stefan. So the big invention in our work here was that he found this very old paper that physicists knew about forever, but we didn't know about that from the scientific, all the people in scientific computing weren't really aware of this, but this classical result on random walks on lattices that we could use to put together to find this diffusion time, this mesoscopic time until two particles on a grid meet in the same voxel for the first time. And this one, as we know, it diverges. So n here is the number of voxels. So it's been rewritten in not in age, but in the number of voxels. But both of these in 3D and 2D, these times diverge as the number of voxels increases. And this is obviously the reason for this breakdown. I mean that it becomes infinitely, the likelihood of actually finding each other vanishes as the mesh size grows. But anyway, then these two are known on the mesoscopic level as well. So then you can just, so what we did then is that you assume, which is quite a natural assumption, that the mean time until two molecules react on the microscopic model and on the mesoscopic model, they should be the same. Seems reasonable. And then you actually obtain a smallest mesh size for which this can hold mathematically. And it turns out that in 3D, this is 3.2 times the reaction radius of the molecule. And this was actually the same if this comes out of Urban and Chapman's analysis as well. But that was kind of lucky that happened. And then in 2D, you also get 5.1 times the reaction molecule. So this is really a hard limit on the accuracy of the RDME. And what this means is that above this limit, you can come up with multiscale rates where you introduce a scale dependency in the reaction rate. But if age becomes this value, that is no longer possible. Essentially then, even if you take the reaction given collision to infinity, it still doesn't cover the case. Did you have a question?
I didn't understand. How did you get this 3.2? Do you compare the lattice with the continuum things, or where it comes from?
Yeah, exactly. We have this.
Log n is just because you make the lattice size so small. So of course the time goes to infinity.
Exactly.
This is also
So it comes by essentially, maybe I was a bit backward, but essentially what this analysis gives you is that it gives you multiscale propensity functions. That if you choose the mesoscopic rate in this form, and this is done by matching, by what I said, matching, saying that the microscopic binding time should be the same as the mesoscopic. We had all the expressions for those. That essentially means that we have to match, in the limit of diffusion, perfect diffusion control, have to match the binding, the mean passage time, or the time until two molecules meet on both scales, on the lattice and in the continuum-based model. And those were known. So by us doing the algebra, and we can look at the paper if you want, then you arrive at these kind of rates. And then this essentially, they diverge for H star. So then they go to infinity. So it's more of a mathematical argument that kind of pops out of the algebra. But then what that also means is that if you pick your binding rates in this form, you always match that. You have the same mean binding time on both scales for any choice of H. And this is what you see in this figure here. So this is for the irreversible case for two particles binding. And there we sort of compare then if this dotted line here is the pure microscopic binding time. We can see that first of all the Collins-Kimball expression here in 3D does a quite bad job over a wide range of grid sizes, but presumably sort of approaches the correct value for H becomes large. And here are some other rates that colleagues of our devised. So you see the rates Sterpone and Chapman derived, they also match the binding time in 3D over the entire range. And the same of the rates that we obtain with this analysis. And then in 2D as well, it's a bit more noise in the simulation, but you also see that you match this time quite well over the entire range. And I mean, it should be clear here that what we match is the mean binding time. Of course, other microscopic properties might be off, but this was the basis of the analysis. This was what we required it to do. And then, in a series of papers, essentially, Stefan and I extended this to the reversible case because clearly we cannot model with just one irreversible reaction. And it turns out that the exact same limits hold also in the reversible case. We have to put some additional assumptions in our analysis. So we say we match the mean binding time, we match also the mean rebinding time, because we have a reversible reaction now. So this is another criteria we put into the analysis. And we also require essentially that it shouldn't be unphysical in the sense that you dissociate faster on the microscale than on the mesoscale. So this is more a physics-based argument. And then it turns out that the exact same fundamental limits hold, and they actually now also hold for any value of the dissociation rate. So in the irreversible case analysis, that analysis was for when you take the binding rate to infinity. But here it holds. And also Stefan has done work looking at non-local reactions. Then you can actually push the grid size down to the molecular radii and match these times. So you can have an RDME simulation on the same resolution as the Smolchovsky model. And also he did this, and this is partly rigorous, partly empirical, but he can also this kind of also works in unstructured grids. Essentially, if you just plug it in and replaces, because all this analysis was done on Cartesian grids, but if you just replace H by the square root or the cubic root of the volume in these formulas, it becomes very accurate. So that kind of works. So this is, and also if you look at the reversible case, then of course we can also look at rebinding distributions, and you see the same behavior here. That so the yellow dashed line here is the pure microscopic simulation, and then you have a series of mesoscopic ones where the most accurate result is then obtained when you pick the grid size at this critical length scale. If you reduce it below that, the solution or the dynamics degenerate, and if it's larger, it's also less accurate. And this is in both 2 and 3D. So it kind of works, is the message. We also went back and then simulated this example that I mentioned in the beginning from Ten Wolle's work, this map K pathway. And also here we see that if you pick the mesoscopic rates in this multiscale way that we propose, so here also the dashed line again, microscale, Collins-Kimball expression doesn't really work very well. And then as you reduce the mesh size with the rates that we propose, you approach the microscopic solution. So here it's the mesh size is taken to be this critical mesh size in 3D, 3.2 times the molecular radii. So in summary, so where we are right now, essentially all is well. We can solve strongly diffusion limited cases with the RDME. We can't do it with the classical ones, but if we do this multi-scale rates, it kind of works. So that's nice. Down to very close to the molecular radii. If we allow non-local reactions, we can take it down even further. But there's something that feels a bit fishy about all of this, right? So what is wrong? What's wrong with this, the logic in this work? I mean, the question is why, I would say. Why do this? What about efficiency? Is it really like, of course, it's nice if you can shrink the mesh down to the radius of the molecules, but really it's not very much of a...
So in the moment you're getting smaller, of course you're adding to the performance, but still you're adding to the load that the simulator.
Yeah, exactly. So I mean, we can now have a microscopic lattice-based model on the RDME form. That's very nice that it works. It's nice that that you have some sort of approximation properties. But really, if you run these simulations, the mesoscopic one at that scale is usually much slower than the GFRD method, because you have a lot of hops. So maybe you end up with millions and billions of voxels essentially, if you try to do this. So even running these experiments for the paper, I mean, is based on Stefan has made very highly optimized custom special RDME solvers that doesn't really do the next sub-volume. It tracks particles instead. So it's something we call next particle method that you can use to speed things up and don't represent the mesh explicitly, use logical expressions. So even to get the comparisons, you have to do a lot of tailoring of the RDME. So that's the point. I mean, this is what I meant. What is wrong? There's nothing wrong with the theory. It's more like if you're a modeler, why would you like to do this? You could have just have taken the GFRD code and ran that. I mean, it was fine. But why we wanted to do this in the first place is because we wanted to do hybrid modeling. So if you have a larger model, typically like this map K pathway, only one of the reaction pairs actually need this very high resolution. So if you can resolve that reaction pair accurately, you can do the rest on a much coarser grid with a mesoscopic model. And then you can save a lot of time. In order to do this, it's nice to know that there is a way to match the two models so that we compute the same thing. This was not the only reason we did it. We also thought it was fun. It was fun to do this analysis. But it's sort of really the case of hybrid modeling. And this is something we have also done. And we actually did this before we did this theory. So the main idea there is that you blend simulations together. So you have some of these reactions occurring on the grid in the mesoscopic model, and some of them on using GFRD. And essentially just, we can also divide space, but I'm not going to talk about that. There's a lot of work in hybrid methods where you put, say, interfaces and use different methods in different parts of the domain. That's also an interesting problem. I'm more interested in the one that talks about capturing this diffusion limited range. So we divide molecules in mesoscopic and macroscopic parts, and then essentially evolve the system with operator splitting. So you take a small time step, you do the mesoscopic solver, a small time step, you do the microscopic, typical multi-physics simulation. We use this NPM. It turns out that was actually something it came out of this work, that it's actually quite switching from tracking sub-volumes for a lot of models that become fine grid. You actually use this kind of tailored method that Stefan implemented. The next particle method is a bit more efficient. So we use this also because it's also especially in the case of hybrid methods, becomes easier to switch between the scales, less updating of data. So you can have a common data structure for the particle list, for example. So it's advantageous in that sense. So we did this MapK example in 2012 as well with this hybrid method, and already then we saw that, yeah, sure, you can recover the full GFRD accuracy with just a fraction of the molecules on the microscopic level with quite substantial speed-ups. And then we waited and we thought about releasing software, and we waited, and then we didn't really want to do that because we felt that, well, the only reason we were able to do this hybrid simulation is because this model had been studied in extreme amount of detail and simulated with GFRD. So the only reason we could make this partitioning was because we knew what the results were going to be. And that wasn't very nice as a black box tool. But then sort of when we did this analysis for these multiscale reaction rates, the rate theory, we sort of realized that out of this can also pop an a priori error criteria. And I don't want to bore you with all the details in the analysis, but it turns out that you take the relative error. So essentially the error, we define that as the error in the microscopic binding time versus the mesoscopic binding time. So the same quantities I talked about before. If you do this and you plug that into this kind of analysis of the reaction rates, it leads to a quite easily evaluable criteria. So if you just know the mesh size age, and if you know the error tolerance, you pick an error tolerance, maybe 5%, you can actually go over all the reactions in your model and evaluate this criteria to just determine, can this actually be recovered on this grid resolution. So in the software, then you give the mesh, you give an error criteria, and then the algorithm can actually partition. So this was another nice thing that came out of the analysis. So now we have a code. It's based on, it's related to the URME framework, but we have switched and worked a lot in Python, so we only have support for this modeling layer in the Python version. Something we could extend, of course, with a MATLAB interface. But essentially then you can, we sort of show in the paper about this, that we can recover binding time distributions or rebinding time distributions with this hybrid method across a lot of different mesh ranges. So essentially it becomes as accurate as the microscopic simulation. An interesting aspect of this, though, because you have now a method that lives both on a grid of a certain size and also with particles. So now the parameter we haven't worked out exactly how to choose, because this is no longer a mathematical problem, it becomes a computer science problem. Is that if you think about it, you actually have an optimal mesh now for efficiency. So you put in your error tolerance and a mesh resolution, and then you get the number of particles that become simulated on the microscopic level, and so on the grid. But if this is the number of voxels in your mesoscopic mesh, of course, as the mesh becomes finer, we know that we can capture the microscopic dynamics on the grid. But then also the cost goes up, the execution time goes up, of course. And as the mesh becomes coarser and coarser, eventually all the reactions will be flagged as microscopic. Because at some point all the reactions become too diffusion limited for that grid resolution. And that means that the execution time will sort of have this kind of optimality behavior. So somehow we should pick the mesh resolution based on optimal efficiency. So all of these have the same. All of these simulations here have the same accuracy, but the runtime varies. So this is a little bit interesting. So when did I start? 4. Was that 4? So maybe 10 more minutes. Yeah. I will share this with you in confidence. So this is our latest result. So we thought that okay, if we can cover the if we can have full accuracy on the mesoscopic grid, one alternative, of course, to do a hybrid method where we blend the particle-based with the mesoscopic method is to do a pure grid-based one, but with different grid resolutions. So this is something we call hierarchical RDME, and this is current work. So these are results from today that Stefan sent me earlier today. And also for this favorite map K example, it's not, yeah, now I'm diverging here, but it's not obvious to me that the reactions are that diffusion controlled in biology, but that's something maybe a physicist can help me uncover. But anyhow, here we instead, in this method, we instead we use a sequence of meshes, and then this criteria also allows us to put in the mesh resolution and tell us what reactions should be done on each level. And then reactions can happen between molecules on different levels. So, but that's fine because accuracy is always limited by the coarses grid. So if you do this really fast reaction will occur in a very fine mesh, and then the others one will successively use coarser and coarser grids based on this error tolerance criteria. And here, this is a very structured computational method. So here we can actually achieve preliminary data that says 100 times faster than the latest release of modern EGR4D that you find on the web. Obviously here, this is a nested hierarchical grid-based method, so it's not going to be very easy to generalize to complex geometries. So again you see the trade-off between simulation cost and modeling flexibility. But still it's pretty fast. So I thought that was a bit fun.
Is this multi-grid?
It's not a multi-grid, it's a multi-level method. It's not related to multi-grid methods. But it uses multiple meshes at different levels, and then particles move between these levels depending on whether they are close, for example, to a molecule they react with for a very diffusion control reaction or not. But it's not multi-grid.
How does this relate to multiples where you have exactly the same concept to some extent? You have different levels of grids, refined to costly.
Yeah, but we can discuss that offline. I don't think it is the same thing, but we can delve into that. Yeah. So that's all I wanted to say about particle-based and RDME simulations. Questions about that?
Just very quick. So you're solving PDEs here, reaction diffusion equations, and
No, not PDs. We're not solving PDs.
but in the limiting case, when you check when you refine H and as well as T, you can show that you have the reaction diffusion model in the limiting case.
It's a reaction diffusion master equation.
So yes, I understand that.
Yeah.
How can you relate? Normally, when you solve these models, your H should be related to the time step that you're choosing for your time solver. Are you concerned about this?
Oh, you mean that are you talking about the splitting time step, or?
I don't know what you use for marking time.
Yeah, it's like operator splitting. Yeah, there is a relationship between the time step and the mesh, and that's also a long story. And I think we can discuss that offline, I think. So we have had two versions of this hybrid method, and in one of them, you didn't really have convergence in time. But this comes from the stochasticity of the problem. So you have some relaxation time that it takes for particles to become well mixed. So then in the first version we did in 2012, you had an optimal time step, and that one was not very easy to find. So in the latest paper, we have Stefan actually fixed that, but then by letting molecules have a lifetime or tracking the lifetime of the molecule. So a molecule has to be, if they are microscopic and going to transition to mesoscopic, they have to stay microscopic for a certain amount of time. And if you do it this way, and then you can shrink the step, and this is in relation to the splitting time step and the grid resolution. And then if you do it in this way, you actually have convergence in time in the delta t there. But it's a good question. It's not at all obvious. It's quite, it's numerical problems. Okay, so I just wanted to say a few words about this. I know I only have 5 minutes now. So now we switch topic a little bit because we have seen a lot of nice work on multicellular simulations, and this is something I'm not very experienced in, but that we are sort of starting to do more and more in the group, and we saw a nice presentation by Stefan there on a new method. So I have and this comes back to this e-science, cloud computing. So I have a student, Adrian, that is quite interested in cloud computing, parallel computing, and he kind of works on a framework called Orchestral, and this is also work in progress. We have one conference paper out, and we plan to do a lot more work in this area. But I wanted to share it with you because even if it's an early stage, maybe you have ideas or suggestions there. So the objective of this is to create a framework that makes it easy, or as easy as possible, to take different models for single cell kinetics, because we have many of them. So we have these 2 models, but there are more, and then for every model we have 5 good pieces of software. So this field is quite mature now. So we have talked about modern EGFRD and Uhrmacher, and we have talked about Smoldin and others. And people want to try their favorite tools or the tools that they believe in and put them together into complex simulations. And this is the thing we're trying to solve with this framework then. So how to express cell-cell signaling simulations based on single-cell simulation tools, and also to do that in a way that we can automatically generate highly scalable parallel simulations that also are able to leverage commodity resources in clouds, for example. So what I talk about cell-cell communication right now is that I talk about sort of touch-based signaling like Notch, where you have actual molecular communication across cells in adjacent to each other. And essentially we want a framework that can help us bridge these scales, and this implies multiphysics modeling. So we have some model for intracellular signaling or intracellular kinetics, and then we have things happening between cells. So maybe this becomes, if you look at a fine scale simulation like the RDME, so here are 2 cells then represented as polygons. So we have some intracellular model, and then there is something happening on nodes between the boundaries, or in general on the boundaries. And then this has to be scaled up to multicellular frameworks, and eventually to 3D and different types of maybe center-based models or vertex models. And the problem we see here is that, but also an opportunity, is that there are many different models and tools that can model all these individual parts. And we're not trying to propose a new one, but for example, we know that, say, ODs are quite used in CTMC rule-based for cell signaling. All these kind of tools we talked about, but there's also very many different ones for mechanics. At least we haven't found a consensus in the literature as of which is the best model and framework to do when to simulate cancer tumors or other types of complex emerging behavior. So as I said, we try to put a framework that can put things together and simulate it. And we haven't gotten super far, but we have a software release. And essentially it's a simple structured framework where you as a user, you define a cell interior model, and this is a bit up to you to choose the tool you want to use for that, and then you describe the reaction network in the language of that tool. You also have to define a boundary model, so you define a model what happens on the cell surface or the cell boundary. So if this is a polygon, it will be edges. If it's a sphere, it will be the surface. We have done this for polygons now, for vertex. Yes?
So,
Is MCell doing this as well? No, I didn't know that they had moved into that. But I will check that.
But you just do it exactly
I will.
what I propose to do. You can create any shape, it's a distribution of proteins, just diffusion of ligands around,
Yeah.
and the combination. You can do it online.
For one cell or for many cells?
For many cells. It's called M-cell.
Yeah. I know MCell. I haven't looked at it in a while. Does it also automatically create parallel simulations in the cloud?
Yeah.
Okay, then I will look at it. Then it sounds like very similar effort. So I will take a look. But I bear with me, I will finish here then. But essentially you put this in then, and then the framework implements an orchestrator based on operator splitting or co-simulation that updates these models, and you also have to tell how to transfer data between models. Does MCell do this for any type of tool or their own tool? Because here the objective is that one of them could be this could be a single cell simulation interior with MCell, for example. Yeah, and this could be an RDME on the boundary.
I use MCell just to study simulation between two cells.
Yeah.
Like one cell release some ligands.
Yeah, what I'm saying, MCell has a very specific algorithm for how they do reactions, for example, or at least they did in the past. So here I'm trying to make it general, but yeah, let's see, I will check. Yes, and then this orchestrator kind of deals with creating a parallel task graph and running this in parallel over cloud resources. So we have done one example where we took this modern EGFRD and we made very simple case. This is 32 by 32 grid where each of the cells here are, and they are not moving, they're not doing mechanics at this point, but they are fully resolved GFRD simulations, and then there is a communication module between the boundaries. And I'm not going to show you the code, but I encourage you to go and look at our webpage how this example looks like, because Adrian has done a good job at trying to make it simple to express these communications. So what we have studied, and this was in cloud, more focused on the parallel cloud computing, is that we used a framework called Dask, which is a very nice framework for essentially interactive parallel computing in Python that plays really, really well with cloud native computing technology. And what happened, we sort of looked at the scalability of simulations when we scale weak scaling. So essentially we increase the size of the model, the number of cells in the model, as we increase the number of computing resources. And we saw very, very sort of nice scaling to the number of cores or virtual machines. So we can really speed up these simulations using parallel computing resources. And when I say nice, I mean nice in the sense that orchestral is lightweight. It doesn't add overhead, a lot of overhead to the actual simulation. So you see, of course, there's a decrease in efficiency as you go to increase the number of virtual machines. But here that is really limited by performance of the Dask task queue framework. So these are sort of shows Dask, pure Dask latency in the scheduler. So essentially this orchestral framework can express these models, and then you can scale them out, in this case, close to the performance that is set by the parallel computing framework that we use. And then the idea is that also this orchestrator, if you're a computer scientist like you do parallel computing, you can work on the orchestrator engine without having to know a lot about the models. And if you're a modeler, you can skip this orchestrator part and kind of work on expressing or modeling how should cells communicate, or what should the transfer of information, for example, on the boundaries be. What should that model look like? So that's the main idea, but maybe MCell has solved it already. Let's see. Yeah, that's it. Like I said, we're gonna put more solvers in here. We have mechanics with Stefan's new method in a branch there that kind of works as well. And the objective of this is not to run GFRD simulations in every cell in 1 million of cells, because that's probably not necessary. But we want to do that to have a gold standard simulation, so we can then do multiscale modeling based upon bottom-up modeling. So they will also be extended here to support some sort of a way to specify as a modeler, how criteria, for example, when you can switch between, say, a well-mixed model and a spatial in your tumor, or also ways to express this automatically if you have criteria based on error analysis. Yeah. But this is very early work, so feedback is very much appreciated. Yeah. Yes.
So this is not my field of work, so therefore perhaps a naive kind of question. You had this MAP kinase as example, yeah, but you only showed the ERK double phosphorylation. Can you deal really with the full cascade, starting from membrane-bound RAS via RAF, via MEC, via ERK, double phosphorylation, negative feedback from ERK to and so on and so on and so on? A little bit of PI3 kinase perhaps. Is that possible? So how many reactions can you deal with in the end?
If you can use the RDME and a reasonable coarse mesh, we can deal with a lot of reactions. Yeah. Actually, so the tools today are quite efficient. So I think you can. There's no problem in putting all of that in. The more you put, the more expensive the simulator will be. But you can do that, and you can have internal geometries and that kind of stuff. And is it then simulation for? I don't know if you talk about 10 reactions, which are perhaps on different time scales. You have a stiff system. Does it mean simulating for days, weeks, months, years? No,
or?
Not if you can use the mesoscopic model. Then it's usually minutes if you have a fine mesh. Okay. At least with Stefan's latest release of the core solver.
Okay. Thanks.
But there's no. I mean, it's really hard to answer that question in general. But typically when I do these spatial simulations for HES1, for example, we're talking about seconds to minutes to simulate, say, an entire cell cycle of that kind of time window. But that's assuming we can have a mesoscopic mesh. If I need to go to these microscopic ones, and then for the hybrid method, it should, in theory, be able to bridge that gap if you have some very diffusion control reactions. But we haven't tested that on very large models. The mesoscopic one, it runs routinely on quite complex ones.
Thanks.
Yep.
Maybe directly, when you talked about this kind of framework that you are now trying to develop, or that you are thinking about, that you are plugging in different kind of of models, and I was wondering, when you're running them in, for example, parallel, then you have possibly also different kind of meshes. Then you have to come up with kind of like ideas how to combine these, how these things are communicating with each other, not only by means of some kind of species being involved in different kind of reactions, but also referring to space where they are coming together. Have you given this some, how you dealing with these problems?
So maybe my slides disappeared. So I mean, the implementation we have now works for general polygons in 2D, and then there is sort of encoded in this kind of framework. If you look at it, you have to go and look at the code. I can look at that with you, but essentially you have an encoded list of, a cell list that encodes the neighbors. So we always know which two cells are actually interacting, and then what we have implemented so far is that cells can communicate with one neighbor. So there's a one radius neighbor.
So that is.
But then we have, the idea is that you have separated boundary segments. So there's a list of boundary segments and a list of interiors, and then we know the topology of this. So we can also then, when we run in parallel, you have a completely perfectly parallel step, where, like Stefan hinted at in his talk as well, that you can update interior models independently of each other during the time step. Assuming the time step can be picked large enough, you can have pretty good scalability, because this is also, especially if you look at the RDME type models, there's a difference in scales if you go to 2D and 3D in the stiffness. So the stiffness increases a lot.
So referring to parallelization, you are then kind of like, if you are partitioning, do you partitioning the model referring to space, or do you partitioning kind of like the simulator referring to certain kind of activities to be done in parallel or not? Do you know how the partitioning works?
It's partitioned in cells, so it's essentially a map-reduced type of computation,
so
where
it's kind of like
first you run all the cell interiors, then you run all the cell boundaries, then you run communication modules, and then at that point there's a reduce stage where you sort of reduce that information.
Referring to
and then Dask actually does the execution planning. So it's
yeah. And maybe also because you're aiming at a more general approach, maybe you would like to look at the European project Compat, which had before another kind of project. They developed their a multiscale framework for having high performance computing on multiple scales. And they also developed kind of like a language, so to combine and let the kind of different models speak with each other. So and they have been around and doing that for close now for 8-9 years. So they have a rather advanced tool suite there. And so,
so maybe
that
we can
would
use
be
that
because they are not limited to cell biological application, although cell biological application is one of their application areas, so they are also looking in the physical applications and things like that. But nevertheless, from the point of view, maybe it might be interesting to check simply how they approach certain kind of problems that might reoccur in your context.
And I should mention that the reason we started doing this was not, I mean, this is how I presented it, that we have this general framework. Really, we want a high fidelity simulation. That's how it started. We wanted something simulated on the highest spatial resolution that we could afford, because then of course we are going to do multiscale modeling here in ways that we haven't done yet. But then we thought it could be nice. But could you send me a link with that? It sounds interesting. Maybe we can use those tools. Thank you. There's always a risk when you go into a new area that you have missed literature. But yeah.
So I just wanted to hear if you have a comment on the issue of imagined accuracy that I mentioned in my talk. So when you're looking at accuracy, like you mentioned clearly that you kind of think of the GFRD as the ground truth, but actually there are assumptions also in GFRD. You have spherical particles, and in this case this MAP kinase maybe actually turns out that it has a polarized molecule, and actually it's not spherical or whatever. And the same goes for the split step. There's a small error and yada yada yada, and then there comes a MD, molecular dynamics person, who says that no, you cannot do this as very coarse, and maybe there's a quantum what have you. Any thoughts? I mean, in the end, what is the truth, or what is the...
I think a lot about that, and it usually gives me anxiety. I mean, it's,
I am happy to hear that.
No, but I think you have to be a bit pragmatic, right? I mean, obviously there are always assumptions. There's no guarantee that the Smoluchowski model is the best gold truth. It's one that we picked because it's a general consensus, I would say, that it's better with hard spheres than with point particles, and this was one model. I think you could have done this. I mean, you can equally well use other models, like Sam Isaacson has done similar methods based on DOI models and so forth. This one is nice in that it has a very well-defined mathematical structure that you can analyze. But I mean, obviously, you should always be careful trying to push this to too fine resolutions for reasons that you said. I mean, at some point, you have rotational invariance of molecules and that kind of stuff. We have done some simple, plug in the physics parameters, and you can see that probably if you, even for this diffusion limited reactions, if you stay at least in the parameter regime that they did in the Tenvoldi paper, you still have 2 or 3 orders of magnitude before you have to start caring about rotation of proteins, for example. But it's not more than that. So I think you're sort of approaching a dangerous regime. But on the other hand, I mean, if you want to have numerical methods that are easy to use and that can have some robustness, you have to pick some model and do some analysis, I think.
Other questions? So let's thank the speaker again. So tomorrow we're starting at 9:45, right?